this second session of this 60th birthday conference for IMSC. We are happy to welcome distinguished scientists from all over India on this occasion. And our next speaker is one such, Professor Gautam Bhattacharya, who's director at Saha Institute of Nuclear Physics. And he's going to speak to us about a brief history of the Higgs boson.
Okay. Perfect. On behalf of all members of SINP, I would like to wish you a very happy birthday, which is tomorrow, I guess, to the entire fraternity of IMSC, the present member, the past members, the students, postdoc, everybody. Although I didn't spend much time in IMSC except through, passing through during conferences and meeting people, mostly that, and meeting people outside, I'm grateful to many of the IMSC colleagues in more than different ways. When I started my PhD, within 15 days, I saw an announcement of a ACRC school happening in IIT Kanpur. I wrote to the director of that school, RR, who is sitting on the first row, and I was then 15 days old in research, well, whatever research in 15 days, and he accommodated me. So I'm thankful because that gave me a kind of opportunity to meet other future colleagues and friends forever. I mean, those who I met during the ACRC school. As you know, I mean, within first 15 days, you learn almost nothing. So one of the first courses I have ever had in particle physics was given by Murthy, who is here, probably here. Yeah, I saw him at least during lunchtime. He is around. Well, I'll come back to my reminiscences about IMSC as I proceed. Last time I gave a talk on this podium was during WEP, which is a high energy particle physics conference series, which was organized by Rahul, our friend, who is probably watching from somewhere up there. And I'm thankful to him for giving me an opportunity to give a review talk in WEP. Okay, so today I'll not talk about the nitty-gritties of science or particle physics as such, but we'll talk about the historical developments of some of the things that eventually led to the discovery of the Higgs boson. Okay, so I'll take you 100 years ago, approximately, when Maxwell's electromagnetism, Einstein's special relativity, and quantum mechanics were working too well. Quantum electrodynamics, which was created from the union of these three to describe how light interacts with atoms, faced an ugly roadblock. Now, well, I mean, as we all know, I mean, this slide almost everybody knows, that the vacuum, the way we describe vacuum in quantum field theory is not empty, but it is bubbling with temporary particle-antiparticle pair, and the interaction of photon with those transient particle-antiparticle field distorts the electromagnetic field itself. This happens because quantum mechanics allows for non-conservation of energy for a very short period, delta t, as long as, well, by an amount delta E. Now, when people calculated the mass of the electron and the charge of the electron, then after summing up all the possibilities, including the intermediate virtual particles in all possible ways, they found the result is infinity. And that is the ugly roadblock I mentioned. In 1947, the year we became independent, 75 years ago, in a Shelter Island conference near New York, Lamb, American physicist, he reported a measurement of a split of 1 part in a million in the electron energy levels in hydrogen atom, which according to Dirac equation should not have been there. Now, using quantum electrodynamics, people tried to calculate it, and they again found infinity. So in that conference, which was convened by Oppenheimer, he asked two young, extremely bright physicists, Schwinger and Feynman, and there were others as well, to work it out. I mean, to tame this infinity. Now, Schwinger did it in his own way. Feynman did, as usual, used his trick. And finally, the conclusion was the following. You try to calculate the mass and the charge, you find infinity. The expressions look very similar when you try to calculate the splitting in the hydrogen spectrum. Now, you replace that infinity by the measured value of the mass and the charge. And so, replacing the infinity by the experimentally measured values, you can reproduce, actually they did reproduce the anomalous magnetic moment of the electron. The technique of using known values, which are experimental values, to calculate other values eventually became known as renormalization. Meanwhile, development in gauge theory took place. Now, QED is a gauge theory which relies on invariance under a gauge or phase transformation at each point in space-time. And the carrier of these electromagnetic force is photon, which we will call a gauge boson. Now, gauge invariance means that regardless of the scheme of accountancy, that doesn't matter which way you calculate, you end up getting the same result. Okay? And it's a profound scheme that causes the electromagnetic force to exist, and it ensures that photon is strictly massless. Then people tried to include more particle. Instead of one electron, they used a pair of particles, for example, the neutron and proton, I mean, just as an X and Y, for example, more than one fermion, and they tried to construct the QED-like model, but because now the algebra involved matrices, more than one photon-like object emerged, and some of them are charged, electrically charged. At the same time, the role of weak interaction was realized for example, in beta decay, as well as in explaining why we get daylight from the burning of the solar fuel, and that required a massive, not massless, electrically charged gauge boson. In the I think in 1957, the V minus A nature of weak interaction, which was proposed by an ex-director of IMSC, Sudarshan, and his PhD supervisor, Marshak, and more or less at the same time by Feynman and Gell-Mann. There was, stories, I'm not going to get into that. But there was realization that electromagnetic and weak interaction may have some common connection. But the problem was that to explain beta decay or to explain radioactivity, you needed a massive charge gauge boson, but the mass is incompatible with gauge invariance. How to reconcile gauge invariance with massive gauge boson? If you include the mass by hand, the infinities will bounce back. So the message from the previous slide will go. So we have to realize these two things. I mean, to reconcile gauge invariance, at the same time, we have to have a massive gauge boson. It's apparently disconnected idea, but we'll see how they are connected, is the concept of hidden symmetry. Now, you all know about this Salam's banquet, that if you sit in a round table, although there is a symmetry, I mean, if you sit here, you can choose one from the left, one from the right. The moment you make up your mind and choose from the right, everyone else will have to choose from the right. Okay? So the symmetry is broken. Similarly, if you go sub-zero to sub-zero temperature, the full rotational symmetry of water molecules is reduced to discrete symmetries. In this case, the 6-fold discrete symmetry in the form of the snowflakes. This is the idea of spontaneous symmetry breaking, which says that somehow transition from a phase with full symmetry takes place to a phase with lesser symmetry. Similar things happen in the context of superconductivity, where the symmetry that is hidden is the gauge invariance of electromagnetism, and which leads to organized Cooper pair bonding. Well, I mean, there are similarities and dissimilarities to the context I'm going to get to. Essentially, in superconductivity, I mean, BCS tried to explain the dynamical feature of it, that the two electrons seem to attract each other near the Fermi surface. But what is important in our context is symmetry breaking and the unbroken subgroup. Okay? So the unbroken subgroup in this case is a rotation by, well, by 180 degree, which says that you have to replace E by minus E, and which means an even number of pairing of electrons can get an expectation value, which gives rise to Cooper pair bonding. So essentially, with the help of the symmetry breaking and what is your unbroken subgroup, one can justify the zero electrical resistance and exact flux quantization. But BCS tried to explain the approximate dynamical symmetry breaking in a different context. So in our context, the symmetry group and the unbroken subgroup is important. Okay, so Nambu realized in the early 60s, as well as, Goldstone, that, and in fact Goldstone gave a rigorous mathematical proof that whenever there is a spontaneous breaking of a continuous, not discrete, continuous global symmetry, massless bosons would appear, and they are called the Nambu-Goldstone bosons. This Mexican hat potential we have seen in the textbooks. It says that the Goldstone bosons, which are massless, correspond to the degree of freedom along this zero, the orbit of minimum energy configuration. If you try to stretch the orbit, you need energy, and that is a massive mode. So, so the question is, where are those massless modes? Experimentally, there was no evidence. So there are two problems. One is the problem of having massive gauge boson to explain radioactivity. How do you reconcile mass with gauge invariance, and so that the infinities don't hit back? And the second is, where are these massless bosons if you try to connect these two ideas? So whether it's a problem or an opportunity. So these two problems together can lead to an earth-shaking solution. Well, this is the only mathematical equation I have in my slides. So essentially, the Goldstone modes or the Nambu-Goldstone modes correspond to these ones, which are in the, for example, in this Mexican hat potential case, this mode corresponds to the one in the exponential, whereas if you try to stretch it, the mode that corresponds to stretching of the orbit is the sigma, which will be massive, and V is the order parameter. Okay. Now, there are two issues then. One is the generation of the gauge boson mass, okay, and another thing is what happens to that sigma, namely the massive spin zero particle. Now, on this slide, I will probably spend a little bit of time that Anderson, he said that in a superconductor, electromagnetic field is short ranged. I mean, photon is massive. It simply means that the following, that how to give an example. Suppose we are driving through a tunnel, then because of the metal on the tunnel, we see that our radio signal is not weak, is not good, I mean, is weak, which means that, electrical field has a problem, has a distortion coming through the metal, but the compass still points to the north, means there is no problem with the magnetic field. Inside a superconductor, both electric and magnetic fields are repelled. Okay, the repelling of the magnetic is the Meissner effect. So which means the electromagnetic field leaves on the skin of the superconducting surface, and because it is short ranged, the corresponding carrier appears massive. So photon is massive, okay, inside a superconductor. Now, Anderson thought of a plasma in which that the photon becomes massive inside a superconductor in the following way, that the zero mass of the photon in quantum electrodynamics and the massless Goldstone boson arising from spontaneous symmetry breaking, they marry each other. So 1 degree of freedom is lost due to the fact that the Goldstone bosons are not seen by us, which reappeared in the form of the massive degree of, well, massive mode, I mean the 3rd degree of freedom for the photon. Now, the embarrassing massless boson, the Goldstone boson, is avoided in a non-relativistic plasma. So that was Anderson's idea. Now, Klein and Ben Lee, so they said that the Goldstone theorem tells you that the massless mode has to be there, okay, if there is a spontaneous symmetry breaking. The embarrassing thing is that it is not experimentally seen, or it will have catastrophic consequence. It is not there. So where has it gone? So Goldstone theorem fails in non-relativistic theories. That is what Klein and Lee said, okay. Anderson's superconductivity is a non-relativistic phenomenon. But they also said that this argument holds in relativistic theories as well. That is not correct. Gilbert, now I'll talk about him. He was a, I think he was a PhD student of in Imperial College of Matthews. Matthews has a Chennai connection. He was born in Chennai, and he gave a no-go theorem. He said that the presence of Goldstone boson cannot be avoided in relativistic theories. Okay, so it's a no-go theorem. So that means it's really a roadblock. Okay. Now I'll talk about Gilbert a little later. Now, American Brout and Anglaire, François Anglaire is Belgian. So Brout got a remarkable postdoc in Anglaire, and they elevated Anderson's assertion from Kunz matter perspective. They approached the thing mostly from Kunz matter point of view. They said that in relativistic field theory, they required a massive scalar boson. They didn't emphasize on it, but they mentioned about the mass generation mechanism exactly the way, roughly the way, I would not say exactly the way, roughly the way that I described before, that photon is massless to start with. It eats up the Goldstone boson and becomes massive, okay, and the massless Goldstone boson disappears. That was Brout and Anglaire, and they wrote their paper in summer months of 1966. I mean, these months are important. A few months later, Guralnik, Hagen, and Tom Kibble, they wrote a similar paper that Goldstone boson need not be present in locally conserved theories. Locally conserved theories means gauge theories. And the force carrier is like photon-like object, like for example, which would eventually be known as W, is a charged gauge boson in beta decay. They become massive. I was telling you how they become massive, because radioactivity requires massive gauge boson to mediate weak interaction. They become massive by eating up those Goldstone bosons. So they concentrated only on mass generation of the gauge bosons, and they did not mention about the massive scalar. You remember this, where I have to go. They did not mention about this particular scalar. They were talking about these particular Goldstone bosons. So they concentrated on the mass generation mechanisms, as were Brout and Anglaire. Okay. Peter Higgs came within a few months in the picture. So he said, so what he did, he avoided the no-go theorem. He obliterated the no-go theorem of Gilbert. Gilbert said you cannot avoid having a Goldstone boson, and that is the embarrassing situation because nature doesn't have it. Higgs said, yes, of course, Goldstone boson would be there, but not in a relativistic theory which contains gauge fields. So Gilbert's argument fails. So this impasse was lifted and massless scalar boson avoided. So you see that up to this point, All these three sets of people, Broughton, Anglia, Guralnik, Hagen, and Keeble, Higgs, they're all similar. They're trying to explain the mass generation of the gauge boson, the mechanism of mass generation of the gauge boson, and that the Goldstone bosons are devoured, they're eaten up by gauge bosons, which in turn massive. But due to some divine intervention, when you get a referee, when your paper gets refused in the first place, and you have a referee who is very helpful, Higgs got a referee, who suggested that what about that massive mode which you have not talked about. Now, in those days, people were, very Brahminic in nature, even outside India. They did not want to talk about a spin zero particle, a hypothetical particle, which has not been seen and nowhere to be seen, whose mass is not predicted by the theory. So it's not that nobody noticed it, but they all focused on the mass generation mechanism. They did not want to talk about that particular sigma. Okay? So Higgs was forced to talk about that sigma, okay, that is the radial excitation, which is a massive excitation, and that is the Higgs boson, which ultimately would give him the Nobel Prize. Again, due to that divine intervention I'm talking about. Okay. Now, I promised that I will tell you a story. So Gilbert started his career as a, what you would say, particle physicist in today's language. But by the time he did his PhD, he was kind of fed up having proposed a no-go theorem. So he got a good recommendations from Salam. He went to Harvard, and he met Watson and Crick on the same corridor where he got an office. He was impressed by their work. He started working on human genome, and in 1980 got Nobel Prize in human genome. On the other hand, Higgs, he did his PhD in molecular physics. Well, he got interested in the no-go theorem. He tried to bypass that no-go theorem, succeeded, and got a Nobel Prize in particle physics. So their path crisscrossed. In the year 1962, the year this institute was founded, Glashow created a model with massive gauge bosons together with a massless QED, which is photon. It is not technically renormalizable, as he put the mass by hand. He only hinted that unification of weak and electromagnetic forces might contain the clue for renormalizability. On the other hand, Salam and John Ward, they independently constructed the SU2 cross U1 theory, but as world experts of renormalization, they understood the gauge theory part far too well, but they were unable to digest the masses of the WZ bosons because that would ruin the renormalizability. Keeble is the person who incorporated, he was very good in mathematics, in group theory, so he incorporated group theory into the idea of spontaneous symmetry breaking. So the marrying of spontaneous symmetry breaking with the theory of Young-Mills theory, the gauge theory, together yielded eventually the right result, that the 2 degrees of freedom of photon, namely the 2 transverse degrees of freedom, plus the 2 complex degrees of freedom of a complex scalar field, were reorganized as 3 degrees of freedom for the photon, namely the 2 transverse and 1 longitudinal for the mass, and 1 remnant, the sigma degree of freedom, the massive scalar mode. So together it is 2 plus 2 is 3 plus 1. So it is very loose way of saying, but Keeble incorporated group theory into the whole idea. Finally, it's Weinberg. Weinberg's name was mentioned in a talk by Rohini. Weinberg used the SSB idea, this spontaneous symmetry breaking idea, in SU2 cross U1 model. Salam independently promoted this model, realizing the significance of the mass generation mechanism, maintaining gauge invariance. And then came 't Hooft. I mean, you can see 't Hooft's picture outside this auditorium. Yes, I mean, he might have come here. I'm sure I have seen him once in IMSC. He might have come here many times. So 't Hooft is different. 't Hooft's the way of thinking is different. Just like Messi plays differently. I mean, it's not that he's a much better player than the others. So 't Hooft thinks differently. he went to Curzes Summer School. And there, Bentley was talking about the unitarization of the sigma pi model, that the pions, which are the Goldstone bosons, if you look at the pion-pion scattering to pion-pion, you need an intermediate sigma, which is the old pi sigma model. So it appeared to Etoft that maybe you need that sigma pi, well, I mean, the sigma denoted is not the pi sigma sigma. So you need the a scalar degree of freedom, spin 0, massive degree of freedom to unitarize the WW scattering to WW. That is, the bad high energy behavior can be tamed if you incorporate a massive spin 0 degree of freedom into your theory. So that will unitarize, that will give a lot of credibility to the standard model. So from the bad high energy behavior can be tamed by incorporating the Higgs field. Finally, in 2012, when the CMS spokesperson Joe Incandela and the Alice spokesperson Fabiola Gianotti showed us those plots, our heart stopped, right? I mean, this bump. We have been waiting for long, and eventually the Higgs boson was discovered 10 years ago. The important thing is that the strength of the Higgs coupling to the pair of gauge bosons, namely ZZ or WW, that was experimentally found to be, related to the Z mass. I mean, this proves the mass generation mechanism. And this mechanism was promoted by Anderson, Brout, Honglayer, Guralnik, Hagen, Higgs, Kibble, Etoft. But only Higgs talked about the Higgs boson. So there was no dispute about that. The sigma particle was talked only by the Higgs, again by the referee's intervention I talked. The disintegration of this particle means the so-called Higgs boson into two photons, and studying of angular momentum of the various decay products showed that it has spin 0. Okay. Importantly, Yukawa force, if not anything, Yukawa force was measured at LHC, and unlike the strong, weak, and electromagnetic force, Yukawa force is not quantized. You can see Higgs and Honglayer, Brout passed away, and Guralnik, Hagen, and Kibble were 3 months late, and it's a rule of 3. So there was no other choice, okay, to share this prize, and Rolf Hoyer is seen with the two eventual Nobel laureates. That day they didn't get the Nobel Prize. But it was sealed, the writing was on the wall. Final outlook. The standard model of Glashow, that was 1962 paper, Weinberg, 1967, and Salam, his set of lectures in Imperial College, is now a standard theory. It shouldn't be called a model anymore. The mass of the Higgs boson is approximately, well, I shouldn't say approximately, it is now so precise that was not thought when LHC was built to find out the Higgs boson. LHC was a win-win machine. SSC was scrapped, so the Americans couldn't do it. So LHC was a win-win machine because either you see Higgs, or in the absence of Higgs, you will see the strong scattering of the WW scattering, you will see with very high luminosity, you will be able to see that. Okay, that is what Etoft said, that there will be bad high energy growth, so you will see strong scattering. So, but with a precision of 1 GeV, nobody attested that. Nobody could imagine that LHC would reach that kind of precision even 10 years ago, okay? Even after the discovery of the Higgs. Today, the precision is even less, okay? Now, the problem is that, I think Rohini mentioned, why is Higgs so light? I mean, 100 GeV. The theory is renormalizable, no doubt, but the theory is not robust. Standard model or standard theory is not robust. If I add a particle which interacts with the known particles, with the gauge bosons or with the Higgs, at a very high scale, I mean, close to, say 10, 15 orders of magnitude heavier than the Higgs boson, then that mass would appear as through the virtual corrections contributing to the Higgs mass. Now, that is the most uncomfortable situation. Now, some people would say, why do you care? There is no such particle. The question is, theory is not robust against the presence of these hypothetical particles. If you look at the evolution of physics, molecular physics does not care about atomic physics does not care about the mass of the nucleon, and the mass of proton does not care about your top mass, okay? So there are symmetries protecting each layers. So in this case, we are looking for fundamental symmetries which would protect the Higgs mass against such bad quantum corrections. And this is one of the motivations for going beyond the standard model, at least to find the stability of the Higgs boson. As Dr. Ramaswamy mentioned, he's not here, that for a country like India, stability is very important. For a model like standard model, which we are trying to claim as a standard theory, stability is very important. So even if there is another source of the dark matter from somewhere, some people claim that it may have a non-particle physics source. Let me not get into that. Even the model itself, from the theoretical point of view, is not quite stable. If you get dark matter from a beyond standard model physics, and that physics can explain the stability of the Higgs, plus some other minor hiccups here and there, we would be very happy. So there are 2 ways to go, or 3 ways to go, or 4 ways to go. Some are more popular, some are less popular. Supersymmetry has been a popular way of going for physics beyond the standard model. Additional dimensions, like additional space-like curl dimension, is another way of going towards BSM, constructing BSM. Supersymmetry is also extra dimension. I mean, it is an extra dimension in fermionic coordinates. So that way, these kinds of space-time extensions, or in fermionic modes or in the normal space-like modes, but curled, give us something. But we have to yet see the evidence of those things. Okay. So the other question is whether Higgs is an elementary particle or a composite particle, and there are plenty of other questions. Okay. So let us not get into that. My job here was to highlight the historical developments that led us here. And one thing somebody said, that we missed many opportunities. So there is one opportunity where, like when the whole world went to gauge theory, we were slow. We did not quite get into that as fast as we should have. One of the earliest lectures came from one of our colleagues from IMSC, Rajasekharan gave a set of lectures on gauge theory application in anomalous magnetic moment of the muon in Saha Institute in the early 70s. It was, I think, RR would recall, I don't know. There was a SINP note by Rajaji on gauge theory calculation in the early days. I mean, we could have contributed more had we been into that game more intensely. Thank you very much.
Thank you. And we'd like to give you a small memento. Our next speaker is Professor Vijay Kodiyalam, who's been in the mathematics group of IMSC for over a quarter century. Vijay.
So at the outset, I'd like to thank my colleagues, the organizers, for an invitation to speak at this 60th year celebration of IMSC. 60 years is certainly a landmark in the life of an individual or an organization, and I've been here for almost half this time, so it's doubly a pleasure for me to speak on work that was done here. So I'm going to speak on picture invariants. So this work was done roughly 20 years back with my colleague Sundar, and so I should probably give a word of explanation as to why I'm speaking about it now. The reason is, very recently, this has found a new application in quantum information theory. So that's what I'm going to speak about. I'm going to speak about the picture invariants themselves as well as the application to quantum information theory. So, and there is a picture, that's a picture invariant. As you can see, it's a directed graph. It has vertices and edges. The edges are colored, and these colors represent various vector spaces. So X is a vector space, Y is a vector space, Z is a vector space, and these are colored in red, blue, and green. And then we have operators, S, T, S star. These operators go from, typically they go from a tensor product of some of these vector spaces to some other tensor product of these vector spaces. So as you can see in that one, T has inputs blue and green, so that goes from Y tensor Z, and it has outputs also blue and green, so it goes into Y tensor Z. S goes from X, that's the red vector space, to blue tensor green, that's Y tensor Z. So I'll get more into picture invariants a little later, but first of all, invariants are certainly very important in mathematics. And if you see even the titles of the talks for this conference, you will see that at least three of the mathematics talks have invariants in the title. So I'll begin with invariants on a very naive level first, beginning with parity. So parity is one of the first invariants that one thinks of when dealing with discrete sets, and it's an important invariant. Many proofs depend on parity for to complete. So here's a simple problem. It's a very familiar problem. We have a chessboard, and it's a truncated chessboard. So you remove the two corners of this chessboard, and you're also given dominoes. So a domino is a rectangle of this kind which covers two neighboring squares of this chessboard. You're allowed to place this domino either vertically or horizontally, and you're given 31 such dominoes. There are 62 squares on the chessboard, and you would like to cover the chessboard with 31 such dominoes. So the question is it possible to do it? So typically one of the applications of invariants is in impossibility proofs. So we want to say that this is not possible. So when I said invariants, parity is an important thing, is usually evenness or oddness, but that's not what I mean by parity in general. Parity is a choice between two things, black and white, good and evil, whatever it is. So here you just color the chessboard in the standard way, and when you color the chessboard in the standard way, you see that the two colors that have been removed, the two corners, are both black. And every domino, no matter how you place it, covers one white and one black. So it's not possible to cover the chessboard with 31 such dominoes. So this is an impossibility proof. But it's also sometimes, if the invariants are good enough, then it can also be used for proving things, positive things. So for example, we can change this question slightly and say, instead of knocking off those two corners, let me knock off some two squares of the chessboard, and of different colors, one black and one white. And then ask, if you're given 31 dominoes now, then can you cover it? And as it turns out, the answer is yes. If you think about it for a little while, you'll see that you can. So this invariant somehow is complete. So we are always going to be interested in invariants and completeness of the invariants. Not in this situation, but in situations which involve vector spaces typically and unitary groups. So let me begin with this first example. Two examples I want to give. So let Q be an operator from R to B. R and B are vector spaces, typically complex vector spaces endowed with an inner product. So finite dimensional Hilbert spaces basically. And Q is a linear transformation from R to B. And we want to see what happens when you modify Q by applying symmetries of this vector space on either side. So U is a symmetry of B. That means U is a unitary matrix of size, whatever the dimension of B is, and V is unitary matrix of whatever the size of R is, and you want to see Q dash is U Q V star. What we want to know is, under this change, what is it that remains unchanged about this operator? What is common to Q and Q dash? And this is a well-known thing. So we know this singular value decomposition. Singular value decomposition says that any matrix Q can be written as U dV star with D diagonal, and its non-zero entries are the non-negative square roots of the eigenvalues of Q star Q. So what that says is, essentially what is invariant here is the eigenvalues of Q star Q. Those are the invariants in this situation, and further these invariants are complete. If you know those eigenvalues, then you know Q up to multiplication on either side by two different unitaries, possibly different unitaries. U and V are possibly different unitaries, and so you can determine Q if you know the diagonal matrix D. Now, instead of saying eigenvalues of Q star Q, I am going to say it in a convoluted way, because this is the one that is amenable to generalization. So knowing the eigenvalues of Q star Q is essentially the same thing as knowing the traces of the powers of Q star Q. If you know the traces of all powers of Q star Q, then you know all the eigenvalues of Q star Q, and so you can determine this Q up to multiplication by unitaries on either side. So these form a complete set of invariants. This is one problem. So let me change the problem slightly and go to what seems like a simpler problem. And this is where you have an operator on a space. So it goes from R to itself. And again, the symmetries of the space, the unitary group of that size, acts on P, this time by U P U star. So it changes P by conjugation by U. And here we can ask, what are the invariants? So looking back at the previous example, so traces, previously traces of certain things in Q and Q star were invariants. Here we will see that the traces of any word in P and P star and the corresponding word in P dash and P dash star are the same, because these two words differ only by a conjugation by U, and so the trace remains invariant. And once again, this is called Specht's theorem. This says that the converse holds as well. So the only invariants, if you know the traces of all words in P and P star, then you know P up to unitary conjugation. Right? So these are the two examples that I want to generalize. Okay, so in order to generalize these two examples, so let's get to the pictures. So I want to represent tensors, or what I mean by tensor here is just linear transformation from a tensor product of vector spaces to a tensor product of vector spaces, and typically it will have some upper and lower indices. So for example, so we have this, so P goes from R to R, so P will have, if you choose basis, P will have some structure constants with respect to that basis. So if I call that Pij, I want to represent this structure constant by a picture of this kind, Pij. Similarly, Q here goes from R to B, so different vector spaces, so I will represent that by different colors. Throughout this thing, vector spaces are colors. Okay, and S goes from R to B tensor G, so that's Sijk, and that's represented by this. Similarly, T. So all of these are pictures of these various tensors, and these pictures form the main the pictures form the main thing in finding invariants for various unitary group actions on these vector spaces. So what can you do with these pictures? One of the main things that you can do is contraction of tensors. So if you are given two tensors, then you can, so in this case I am given this tensor S which has a blue which is going out, and the tensor T which has a blue going in. I can attach these two things, and this picture makes sense. And this picture makes sense according to the following rule. So all these free arrows, the free arrows are the ones which you can wiggle around, which are not attached on both sides, right? All the free arrows you label with whatever I, J, K, L, and all the bound arrows you sum over. So in this case there is only one bound arrow, and that is the blue. So this blue is a bound arrow. So the blue is summed over, so there is a T, and if you anoint this blue arrow with a T, then this evaluates to STKM Tijlt. So that is STKM and Tijlt. So this is the meaning that I would like to assign to such a picture. Okay. Now when we assign these meanings to these pictures, as I said, the bound arrows don't have anything. Only the free arrows have indices. Sometimes there are pictures which don't have any bound arrows. One of the most important ones is this one. So if you have a single operator P and you have this snake swallowing its own tail kind of thing, and this, by the rule that I said, you anoint it with a T and then sum over T. So that just gives you the trace of P, and the trace of P we know is a unitary invariant. So this gives an example of an invariant using these pictures. Okay, so roughly around 2003, Sundar and I proved this theorem, and it says, actually this is not the most general statement, but it's enough for our purposes. If you're given a collection of inner product spaces and an operator which goes from a tensor product of some of these to a tensor product of some others, every closed picture that you can form from several copies of this operator and its adjoint is a unitary invariant. That's the easy part of the theorem. The harder part of the theorem is that these invariants are complete for the action by the unitary group. Unitary group being unitary group, the product of the unitary groups of all these inner product spaces that are involved in that picture. So this theorem, we proved it mainly for applications to subfactor theory. So let me just state the two consequences that we had at that time. One is determination of a complete set of invariants for finite dimensional Katz's algebras. Katz's algebras are finite dimensional Hopf algebras with additional star structure. And more generally, determination of a complete set of invariants for subfactor planar algebras. Subfactor planar algebras are complicated objects. They have infinitely many vector spaces and infinitely many maps between them. And using these picture invariants, it's possible to get a list of numbers which specifies a subfactor planar algebra up to isomorphism. Okay, so this was the work that was done long back. So now let me get to what's the, oh yes. So let me just say what happens when you have a single operator. When you have a single operator, the single operator goes from a space to itself or from one space to a different space. So in this case, Q goes from say blue to red. If you want to make a picture, you take several copies of Q and Q star and then attach them in whatever way you want, such that there are no free arrows left. Of course, you have to attach them so that the colors are compatible. So one example is, so Q star Q, Q star Q. This evaluates the trace of Q star Q squared, for example. But if you have a single color, if both input and output are the same color, then you can take any combination you want, any number of P's, any number of P stars, and arrange them and attach, and you'll get one such invariant. These are not all of the picture invariants. The picture invariants are many more. These are just the connected components of the picture invariants that you get, but that's enough. These are enough in order to be able to distinguish P in that case or Q in this case. So this is a special case of that theorem that I stated. Okay, so now let me move to, sorry, when did I start? 3:27 minutes I have? Okay, fine. Yeah. So here is this thing called Euler's 36 officer problem. 10 minutes, okay. Yeah, 36 officer problem. So if you look, as you can see, that's not 36. There are 25 things there. So let me first explain this picture. So if you look at this picture, there are chess pieces, 5 different kinds of chess pieces. There's this king, queen, rook, bishop, and knight. And they come in 5 different colors, right? Black, red, blue, green, and some kind of magenta, I suppose. So, and this is arranged in such a way that if you look in any row and in any column, all the pieces occur, all the colors occur, and further, there is one piece of each color. So there is this black king, and then somewhere else there is a red king, and somewhere else there is a blue king, somewhere else there is a green king. All possible 25 combinations are here. So apparently the Empress Catherine the Great of Russia asked Euler to solve this problem with officers and regiments. It's basically the same problem, but 6. This is for 5, right? This is 5 colors and 5 chess pieces. So can we do it for 6? And Euler did not quite solve this, but he did say it is not possible. He said it's not possible without actually giving a proof. And much later, about 120 years later, it was proved that this is not possible. This is called Euler's 36 officers problem. Okay, so it's not possible to do the same thing for 6. It is possible to do it for many other things. 6 happens to be an exception. Okay, so let me say something about Latin squares and orthogonal Latin squares. That is the setting in which this problem is currently studied. So, a Latin square is an arrangement of, say, numbers 1 to n, and in a square grid, and every row and every column should have all the numbers. So, like this. So, each one of this is a Latin square. This is a Latin square of just chess pieces. This is a Latin square of just colors. They are not connected for the present. They are two different Latin squares. So, you can see that every row and every column has all the colors. That is a very simple combinatorial object. So, it's known as a combinatorial design, an example of a combinatorial design, a Latin square. Okay. Then there is something called an orthogonal Latin square. These two Latin squares now considered together form an orthogonal Latin square. So, if I go back to the previous picture, if you superimpose this on this and give the appropriate colors, then I get exactly this picture. And this has the further property that all the 25 are distinct. So, that is a property that these two Latin squares together have, and that is called an orthogonal Latin square. So, what Euler conjectured or said was that there is no orthogonal Latin square of size 6, and that was proved in the 1900s. But very recently, a quantum solution for this was found by quantum information theorists. So, let me say what is meant by a quantum solution to this problem. So, the passage from classical to quantum is sort of mediated at a very naive level by these three rules. So, you replace finite sets by Hilbert spaces of that dimension. So, the set with a set of cardinality d, 0 to d minus 1, is replaced with a Hilbert space with a basis d, orthonormal basis of size d, and the symmetry group of this set, which is the symmetric group sigma d, is replaced by the unitary group ud, and things which are distinct will get translated to orthogonal in the Hilbert space setting. So, for example, here is a Latin square of size 4, and here is how you can convert it into something called a quantum Latin square, QLS. What is a quantum Latin square? A quantum Latin square consists of all of these should be vectors in some Hilbert space, in this case a 4-dimensional Hilbert space, and since here we wanted all of these to be distinct in every row and column, here you will naturally impose the condition that they should all be orthogonal in every row and every column. And this is a passage, a very easy passage from a classical Latin square to a quantum Latin square. Of course, if you take classical Latin square and just replace it by the corresponding vector, you will get a quantum Latin square. But certainly, not every quantum Latin square is of this kind. This is very special. These are very special. There are quantum Latin squares, even for 4, there are quantum Latin squares which do not come from any classical one. It's richer. The quantum Latin squares are richer. So, what we want to do is, we want to quantize the notion of a orthogonal Latin square. Okay. And it turns out that the quantization of the notion of an orthogonal Latin square leads to something called a 2-unitary matrix. This is the terminology that is used. I think it could probably be improved, but that is the terminology right now. So, let me explain what is a 2-unitary matrix. So, these 2-unitary matrices are of size d squared by d squared, first of all, for some d. In this case, d is 3. So, in this case, it is a 9 by 9 matrix. And this 9 by 9 matrix satisfies unitarity conditions in various ways. So, for example, here is one operation I could do. I could take each block and write it as a column. So, take each block of that matrix and write it as a column. So, this rearranges all the entries in that matrix. That is one operation I could do. Another operation I could do is each block of this matrix I could transpose. Right, this block gets transposed, the second block gets transposed. I have only illustrated it for the first block, but you could transpose all the blocks of this matrix. That is called a partial transpose operation. And a 2-unitary matrix is one which remains unitary after both these operations. Right? After both these operations, it should be a unitary matrix. It should initially be a unitary matrix, should remain unitary after this and after this. So, this here is an example of a 2-unitary matrix. And this 2-unitary matrix is in fact even better than just unitary. It is actually a permutation matrix. It can be shown that if you have a 2-unitary matrix which is a permutation matrix, that corresponds exactly to an orthogonal Latin square. And therefore, the quantization of an orthogonal Latin square, it makes sense to think of a general 2-unitary matrix as a quantization of an orthogonal Latin square. So, so as I said, last year, not last year, maybe in 2021, April, so there was an article on a quantum solution to Euler's 36 officers problem, which means this is the 36 by 36 two-unitary matrix, right? And this appeared in Physics Review Letters, and this is done by two physicists from IIT Madras, Suhail Radar, Arul Lakshminarayanan, and 4 Polish physicists whose names I'll not mangle. Okay, so what is the solution? I'll just give you a picture of the solution. Here is a picture of the solution. This is a 36 by 36 matrix, and this 36 by 36 matrix, so it has, I've given red, blue, and green entries, and red stands for half square root 1 minus 1 by root 5, etc., etc. These, I should emphasize, is not strictly speaking right. These are only the absolute values. This is a complex matrix, and there is a very fine and delicate tuning to be done with the phase factors of each one of these. They showed that there exists a two-unitary matrix of this kind, thereby solving Euler's 36 officer problem. And this created quite a buzz in the quantum information community. So at this point, we can ask, now it's difficult to construct the solution. So you can ask, is that the only solution? Are there more solutions? So which brings us to what is only solution? What does only solution mean? What distinguishes one solution from another? And a natural way to distinguish two matrices of size d square in this context is by, you say B and A are equivalent, both of them are two unitaries, if B is X tensor U, A, Y tensor V. For unitaries, X, U, Y, V of size D. So pictorially, it is this. So B can be written this way. In which case, one can show that any picture invariant that you can construct from the B is the same, has the same value as a picture invariant that you can construct from the A. And that's easy to see. Together with Suhail Radar, N. Ramadas, and Arul Lakshminarayanan, we recently managed to prove the following two theorems. The first, which is a bit surprising, is there is a unique LU equivalence class of two unitary matrices of size 9. And I gave you one example, that permutation matrix. That is the only one up to LU equivalence. And that uses a little bit of algebraic geometry to prove. And the other theorem, that doesn't use, though, any picture invariants. This other result, for d bigger than 3, there are infinitely many LU equivalence classes of two unitary matrices of size d square. This falls into two cases, one where it is 6 and one where it is not 6. Each requires a slightly different proof. The one where it is not 6 is much easier because we know that there exist orthogonal Latin squares of anything other than 2 and 6. We know there always exist orthogonal Latin squares and therefore two unitaries, which can be modified slightly by changing the phase to get infinitely many of this kind. If D is not 6. If D is 6, then it needs a modification of their solution carefully to get an infinite number of solutions. But this result relies very essentially on picture invariance. So it's quite nice, very satisfying for me that this result, which was proved such a long time ago, has found use in proving this now. And I wanted to share this with you. Thank you.
Okay, I think we'll get ready for the next speaker. So I'm happy to invite the next speaker, who hasn't been around for quite a quarter of a century, but close to it. It's almost 20 years now. Professor Amrutanshu Prasad, who is going to speak to us about Kronecker-Hecke algebras.
I'll just use the board. So, I'm going to talk about Kronecker-Hecke algebras. And this is based on work in progress in collaboration with Raghavan here, Digjoy Paul, and Jyotirmoy Ganguly. So let me just explain these words. Well, these are names of people, but let me explain what they mean in this context. So Kronecker refers to tensor products
or what are sometimes called Klebsch-Gordon coefficients. So what we are interested here are in, we have a finite group G, and a representation of this group is a homomorphism from G to the group of invertible matrices for some complex vector space V. And given two representations, you can take their tensor product. So you can talk about rho tensor sigma, and this evaluated at G will be rho G tensor sigma G, and this will be in GL of U tensor V. Now, a fundamental problem in representation theory is given a group G, classify its irreducible representations. And then once you've done that, you could try to take tensor products of those and try to see how they decompose. So, so what we do is, given two representations U and V, we take U tensor V and try to write it as a sum over irreducible representations W of, we take this tensor product and decompose it into irreducible representations. And each irreducible representation W, the number of times it occurs in the tensor product U tensor V is called a Klebsch-Gordon coefficient or a Kronecker coefficient. And I'm going to denote these by G, W, U, V. So here we are assuming all these U, V, and W are irreducible representations, and they three irreducible representations determine a non-negative integer G, W, U, V. Sometimes this problem has a very nice solution. For example, if you take the group G to be the general linear group GLN over complex numbers or the unitary group, and you look only at polynomial representations in the case of GLN, or you look at continuous representations in the case of the unitary group, then the problem of classification of representations is classically solved from the work of Frobenius, Schur, and Hermann Weyl. And also the problem of determining these coefficients, it's much harder and was done much later by Lascaux and Schutzenberger, and it's called the Littlewood-Richardson rule. So G equals GLNC leads to the Littlewood-Richardson rule. Okay, but if G is the other group which was studied by Frobenius and Schur more than 100 years ago was the symmetric group. In that case, these are actually called Kronecker coefficients, and this is still doesn't have a nice answer like the Littlewood-Richardson rule, and continues to be a problem of some interest to mathematicians, physicists, and computer scientists. So this leads to Kronecker coefficients. Even questions like, can you decide whether a Kronecker coefficient is positive or not? These are difficult problems. Okay, so that explains the Kronecker part, and let me come to the Hecker part. So historically, Hecker algebras are algebras where Hecker operators live. So in the theory of modular forms, you come across these operators called Hecker algebras. and they actually have a nice group theoretic or interpretation which came later. But I'm be interested in a simpler finite analog of this. And so you have a group G, let's say again finite. It doesn't have to be for what I'm saying, but let's just, and a subgroup K. Now this group G, you can construct an algebra from it called the group algebra of G. It's usually denoted by C square brackets G, and one can think of it as just functions from G to C, and multiplication is defined by requiring that f star G of x is a sum over all pairs u comma v such that uv is equal to f x f of u g of v. And this gives rise to an associative algebra called the group algebra of G. And the Hecke algebra associated to G and K, usually denoted by Hg comma K, is just the subalgebra of this. Which has the property that f of K1 G K2 is f of G for all K1 K2 in K and G in G. So this is just a subspace, but you can check that under this product, it actually forms a subalgebra of the group algebra. And this is called the Hecke algebra of G relative to K. If you take SL2QP for G and SL2ZP for K, then the algebra is generated by a single generator, which is a Hecke operator. But here G could be, for example, it could be any group or subgroup. And so I'll give you a specific example that we're interested in later when we construct Kronecker-Hecke algebras. So what about the representation theory of this group? So the idea behind this Hecke operator is to somehow take the elements in the group algebra of G, and this invariance condition is saying that you're sort of averaging over the subgroup K. Okay, so you can think of this also as EK CG EK, where EK is an idempotent operator which comes from averaging over the subgroup K. And what this subgroup, this Hecke algebra captures is a part of the representation theory of the group G, the part of the representation theory which admits K invariants. So irreducible or should I say simple HKG modules, HGK modules, these correspond to irreducible representations of G, let's say, which I'll call V, such that V has non-zero vectors invariant under the subgroup K. Okay, so every irreducible representation of G which has a non-zero vector invariant under K gives rise to a representation of the Hecke algebra. And we have the formula, a nice, well, so this comes from the general theory of semi-simple algebras, that the dimension of this is the sum over all irreducible representations V of the group G of the dimension of the K invariants of V squared. Okay, so both, there may be other ways of computing the left hand side, and the right hand side is representation theoretic. In many cases, the left-hand side is of a combinatorial nature, as we shall see in a moment. So now I want to combine these two ideas, or rather I want to apply this idea of Hecke algebras to try to understand Kronecker coefficients. So now I can define the Kronecker-Hecke algebra, and I'll denote it by Kg. And this is just the Hecke algebra where the big group is the Cartesian cube of G, and the subgroup is just the diagonal copy of G sitting inside this. So this is just G comma G comma G, where G is in G, sitting inside G cubed. And that's, well, certainly a subgroup. And that's called the Kronecker-Hecke algebra. And why is it called the Kronecker-Hecke algebra? Well, recall this fact that the irreducible representations of G, well, I'm sort of overusing now the letter G. So, yeah, but anyway, irreducible representations of G cubed which have an invariant vector under delta G will be the simple modules for this algebra Kg. So, irreducible Kg modules are irreducible representations of G cubed. So, what is an irreducible representation of G cubed? Well, it is just 3 irreducible representations of G tensored with each other. So, they are triples U, V, W, and what we need to know is that this tensor product U tensor V tensor W, this has a vector that is invariant under the diagonal action of G. So, let us just say non-negative. Okay, and now I will explain the connection with Kronecker coefficients. So, U tensor V is sum over W taken G W U V times. So, G W U V, remember I had written this earlier, the same thing, is the multiplicity of W in the tensor product of U and V. Another way of thinking about this is the same as saying that G U V W is the dimension of the invariant subspace of U tensor, V tensor, the contragradient representation to W under the action of delta G. And here I am using a simple fact called Hom tensor duality, which says that the homomorphisms into something is the same as taking tensors with that, and what with its dual, and this is the so what you see is that this I can just modify this definition a little bit and write something G U V W to be defined to be G W tilde U V. And this has the advantage of becoming now more symmetric in the 3 arguments U, V and W. And so, G U V W is just the dimension of U tensor V tensor W under the diagonal action of G. So, so now indeed what you see is that the irreducible representations of Kg correspond to triples U, V, and W, which admit a non-zero vector that's invariant under the tensor product. And what is more, the dimension of this simple module is going to, this irreducible module is going to be precisely the Kronecker coefficient. So this, so what we get is that dimension of Kg, so earlier I had written something of the dimension of the Hecke algebra as a sum of squares, applies here, and this gives sum over U V W G W G U V W squared, sum over all triples of representations U, V, and W of the group G. So, we were Raghavan, Digjoy, Jyotirmoy, and me were working on this, and we were particularly interested in the question of finding groups for which all Kronecker coefficients are 0 or 1, groups with multiplicity free tensor products. And we were trying to understand if we can compute. So one way of thinking about that is to say that this Kronecker-Hecke algebra should be a commutative algebra. And we were trying to characterize such groups, and we have made some partial progress. But coincidentally, at that same time, Bal sent us some preprints by Ben Gelun and Ram Gopalan, who were working on exactly the same problem for symmetric groups. And they were looking at Kronecker-Hecke algebras where G is a symmetric group and trying to understand the Kronecker coefficients using that. And they in fact had this equation in that case, and in this case of symmetric groups, they used what they call ribbon graphs to parameterize this. But let me just come back to that a little more. In the general case, not just for symmetric groups. So this Hecke algebra is parametrized by G cubed mod delta G mod delta G. So the dimension of the Hecke algebra is obtained by taking the group G cubed, modding out by the left and right action of the diagonal copy of G. So if you can count the cardinality of this set, you will be able to count the dimension of the Hecke algebra. And you can kind of simplify this situation a bit, because if you have an element of G cubed, you can certainly multiply on the left or on the right by a diagonal an element of the form G, 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 and make the first coordinate equal to 1, leaving you with only 2 coordinates. And this turns out to be the same as G squared modulo what I'll call simultaneous conjugacy. So this Hecke algebra HKG turns out to be the algebra of functions from G cross G to C such that f of Gx G inverse Gy G inverse is equal to f of xy. So the subalgebra of the group algebra of G cross G, consisting of functions which are invariant under simultaneous conjugation. When you take G to be a group of matrices, this is the dreaded simultaneous similarity problem. However, you can use Burnside's lemma, for example, to compute the dimension of this thing. And in the case of symmetric groups, in the case of symmetric groups, Ben-Galoon and Ramgoolam index these by ribbon graphs. Okay, so I think my time is almost up, so I'll just end with one last result, which comes from viewing these algebras as complexifications of real dagger algebras, which are sort of real versions of C-star algebras. And in the case of symmetric group, this is slightly simpler, but let me write down the general result here. So summation over U V W. Now what I want, I asked Ramgoolam, do you have a formula for G U V W if I don't want the sum of squares, just the sum? And he said, yes, I do. They are in fact some of these things which are fixed by an involution. And the answer is what I call doubly, the number of doubly real conjugacy classes. Where, so an element is said to be real if it is conjugate to its inverse, if there exists G in G such that Gx G inverse is equal to X. And a pair is said to be doubly real if there exists G in G such that Gx G inverse is X inverse, is equal to X inverse if it's conjugate to its inverse, and Gy G inverse is equal to Y inverse. Every permutation is conjugate to its inverse, but not every pair of permutations is conjugate to the inverse pair simultaneously. And this is not quite true in general, while it's true for symmetric groups. And what comes up here in general is the Frobenius-Schur indicator of these representations. Okay, so yeah, so maybe I'll just stop with that. Thanks.
Thank you. No time for questions. You have 30 minutes. Our next speaker is also from IMSC. I have the pleasure of introducing Manjari Bagchi, who will speak to us about studying gravitational physics through pulsars.
Thank
Manjari.
you. So, this, okay, sorry. Good afternoon. So I feel privileged to be here today and tell you about pulsars, which are best laboratories to study gravitational physics, and that laboratory nature has made for us. We did not need to make any laboratory. So what are pulsars? Pulsars are a kind of dead stars called neutron stars. What are neutron stars? When a star, say moderately massive, say like 10 times heavier than the sun, when it dies, what happens? So here first let me tell you what is death of a star. So when a star is alive like our sun, we know that there is nuclear fusion inside it, and because of that nuclear fusion it generates heat, and that heat and electromagnetic waves means that energy is being emitted. That is how we receive heat and light, electromagnetic waves. But then after burning nuclear energy for long time, all the nuclear fuels one day will be exhausted. When that happens, that time there is no more energy generation, but the star keeps on emitting energy. So it starts to cool down. And when it was hot, because of high temperature, there was a large gas pressure. We know from our class 10 physics, PV equal to NKT, right? If high temperature, you have high gas pressure, and that gas pressure balance gravitational pull inwards. So we get a stable alive star. But when the star is cold, means after its death, when there is no more generation of energy, but it is emitting energy. So it is cold, and gravity is as usual because there is no loss of mass. So the star starts to collapse. And that time, if the star is moderately massive, okay, this collapse happens through a explosive event known as supernova explosion. And most of the matter of the star, especially the outside matter, it gets expelled in the interstellar medium, and the inner part, it collapses. And when it collapses, due to extreme gravity, atomic structure breaks. There is no more atoms. So we first get free electrons and free nuclei. Then if the gravity is even stronger, then even nuclear structure breaks. We get free protons, free neutrons, and free electrons. And we know protons are positively charged and electrons are negatively charged. So they attract each other and protons become neutrons. So we get a free soup of neutron gas. And this time, due to quantum mechanical pressure, due to Pauli's exclusion principle, what we call degeneracy pressure, that pressure can balance further gravitational collapse. And if this neutron degeneracy pressure can balance the gravitational collapse, we get a stable stellar system. That is what we call neutron star. And as it is a result of gravitational collapse, and you say the atoms are bigger, now we have only tiny neutrons, they are extremely dense, means so dense that some say you have a neutron star of mass as large as our sun, or maybe heavier than sun, maybe twice the mass of the sun. Its radius is only 10 kilometer. So we sometimes say as analogy that if you can take 1 teaspoon of neutron star matter, it will be as heavy as Mount Everest. So because of this extreme density, the gravitational field around a neutron star is extremely strong. So strong that you cannot explain all the gravitational phenomena around it using your Newtonian classical mechanics. You need to use Einstein's general theory of relativity. That is why neutron stars are such great laboratory to study various applications or theoretical predictions of general relativity. Some people even tried to use neutron stars to test alternative theories of gravity. And this extreme density is one interesting point of neutron star, but that is not the last point. They are also extremely strong magnets. So their magnetic field lies in the range of 10 to the power 10 to 10 to the power 15 Gauss. So I'm sorry, we astronomers are not in SI units. We are in CGS unit. So all my units will be Gauss. I am not going to Tesla. So as the neutron stars have magnetic fields in 10 to the power 10 to 10 to the power 15 Gauss. And to give a comparison, that fringe magnets we all use, those are around 50 or 60 Gauss. So you can understand how strong those magnetic fields are. There is another thing, these neutron stars are extremely fast rotator. Like everything, means like our Earth rotates around its own axis, and it takes 1 day, right? That is the definition, to rotate around its own axis. So all the stars also rotates around their own axis. Like the sun takes 26 days to rotate around, means 26 Earth's day to rotate around its own axis. And the neutron stars can take maybe a few milliseconds to up to at most 10 seconds to make a complete rotation around their own axis. So you imagine you have a star of say, heavier than the sun, it is completing one full spin within 1 millisecond. So that is also a very interesting point, because that also has some implication in gravity study, because when you have a rotating object, that also affects space-time curvature around it. But I'm not going to talk about that, we call frame dragging effect today. So we call this speed period. Speed period of neutron star lies in the range of millisecond to 10 seconds. Now, as we know, the sun or other stars, they emit like sunlight we see. But that is not the only electromagnetic energy sun is emitting, right? The sun emits from very high frequency gamma rays to very low frequency radio. Similarly, all other stars and our dead neutron stars also emit throughout the electromagnetic spectrum, starting from the very high frequency gamma rays to very low frequency radio waves. But there is one interesting aspect, means our atmosphere blocks most part of the electromagnetic spectrum, electromagnetic waves coming from outer space. Only a small window of the optical spectrum and a large window of the radio spectrum, those parts can come to the earth. So that has one advantage. If you want to detect optical signal or radio signal from a star, you can have your detector on ground. But if you want to detect gamma ray or X-ray, you have to place your detector on a satellite and put it top of the atmosphere. So that has the disadvantage, because when you want to place your detector on a satellite, you cannot make it as big as possible, because a satellite cannot carry a very big instrument. But when you are making something on ground, you can make it as big as possible. So like there is one international effort, 30-meter optical telescope. We have very big radio telescopes, 300-meter diameter, or in China 500-meter diameter. So that is why, because you can make radio telescopes very big, studying stars in radio wavelengths, those are gives very precise result. But here you will ask, okay, we understand that all other stars, including neutron stars, they emit throughout the electromagnetic spectrum. But why do they emit at all? Because I said that neutron stars are dead stars. Means first they stopped their nuclear fusion, then they collapsed, then we got. But yes, but today they are dead. But once upon their lifetime, they were alive. That time there was nuclear fusion. There was heat. So they are still hot. So they keep on emitting that residual heat. That is one part. Second reason is, as I said, they are very strong magnets. So there are high energy particle physics phenomena like Bremsstrahlung effect, synchrotron radiation, inverse compton mechanism. So because of that, they emit electromagnetic waves. Then comes one phenomena called accretion. If a neutron star is gravitationally bound to a giant star, then due to extreme gravity, the neutron star can pull matter from its giant companion. And when that matter falls onto the surface of the neutron star, there is very strong X-ray beam. And we know that X-ray, even in our lab, X-ray is generated in that same principle, right? You heat a metal surface or some object through very high energy particle, then you get X-ray beam. It is a kind of similar thing. And that X-ray beam you can detect by placing your X-ray detector on a satellite. And India's AstroSat satellite is doing that very good. But I am not interested in all this type of study of neutron stars. What I study, that is a pulsar mechanism. So I said neutron stars are very strong magnet. And for Earth, like you know, that Earth's spin axis and magnetic axis are misaligned, right? Geographical North Pole and magnetic North Pole are different. So that is possible for any stars, including neutron stars, that their spin axis, means axis of rotation and magnetic axis are misaligned. And if that happens, then when the neutron star rotates, the spin magnetic axis also rotates around the spin axis. And it is the basic principle of classical electrodynamics that if you have a rotating magnet, there will be strong electromagnetic beam will be emitted from two poles. So that is why when you have a neutron star, there is strong beamed electromagnetic emission from its along two poles along its magnetic axis. So now you have a electromagnetic beam, and when the neutron star is rotating, as the magnetic axis is also rotating, so this electromagnetic beam is also rotating. So now it can happen that, say, this speaker is if Earth and the electromagnetic beam is rotating. After one rotation, if it falls onto the Earth and if our detector is on, we can see it. But it is continuously rotating, right? So it will fall onto Earth momentarily, it will move on. Then after one rotation, it will fall on Earth again. It will then move out again. After another rotation, it will fall onto Earth again. So from us, we cannot see anything else. We are seeing only when the signal is falling onto. So for us, we might think that something is pulsing. So that is why the name pulsar came, but it is a wrong name. It is actually we can call it is not a pulsating, but we call it pulsar. It is actually a rotator. So first pulsar was discovered in 1967 by Jocelyn Bell, and as in the morning Professor Rohini mentioned that Vera Rubin did not get a Nobel Prize. Here also it is unfortunate. Jocelyn Bell's supervisors got Nobel Prize, but Jocelyn did not get, but that is the loss of Nobel Prize, not Jocelyn's, right? So also like normal stars or other emissions, they are in throughout electromagnetic spectrum. This pulsar emission is also throughout the electromagnetic spectrum, from radio to optical to X-ray to gamma ray. But for the same reason, you can make your radio telescope on the Earth, you can make them as big as possible. You can observe pulsars in radio wavelength very precisely. So from this point of my talk, by pulsar, I will mean only studying pulsar in the radio wavelength. Here are few interesting radio telescopes. So those are basically like our dish antenna, but very, very big. But these two are in the US, and this is Arecibo, it collapsed 2 years ago. This is an amazing facility we have near Pune, GMRT, Giant Meter Wave Radio Telescope. This is also another very interesting radio telescope. It is at the top of Uti mountain. So we are using this GMRT very much, but we used to use Uti also. That also gave quite good results. So as I said, the first radio pulsar was discovered in 1967. Today we know more than 3,300 pulsars. Most of the pulsars are isolated. There are a few 3-body systems. There are even 4-body systems. And actually first exoplanet was discovered around a pulsar, but that was not very famous because when people talk about exoplanet, people think about exoplanet which is orbiting a sun-like star where life can grow, but the first exoplanet discovery was by pulsar people. And there are about 350 binary pulsars, means you have a pulsar, a neutron star and another star, it can be anything, gravitationally bound to each other and orbiting around the common center of mass. And I like to study binary pulsars because they are the most useful to study gravitational physics. How? Let me tell you that. So first, what we see from pulsars? Yeah, obviously we see the radio signal, but with that, using those radio signals, what parameters we can measure? As I just said that we see the signal once in every rotational period. So obviously by measuring the time difference between two consecutive signal, we measure the rotational period, what we call spin period. But that spin period is also not constant, it changes, which actually it increases. So we can measure that rate of change of spin period or spin period derivative. Why? Because the pulsar is emitting electromagnetic energy, and that energy is coming at the cost of rotational kinetic energy of the pulsar. So it is slowing down and it has a positive value of spin period derivative. And then you, so first two fundamental parameters you can measure for a pulsar is spin period and spin period derivative. Then from your basic theory of emission mechanism, we know these two interesting equations. This is the value of surface magnetic field, which is related to spin period and spin period derivative, means multiplication of that square root and this factor, Gauss, if spin period in second and this is second per second. So that is how we know that neutron stars are very strong magnets, because we cannot go to the neutron star and measure their magnetic field. Also, the age of neutron star are related to spin period and spin period derivative. That is why this type of plots are very popular. Here in the horizontal axis, I show spin period in second, and the vertical axis is rate of change of spin period, means second per second, which is dimensionless. And all those points are different pulsars. You forget those different symbols, those are actually classification of pulsars, so we can ignore those. And those lines, you can see this 10 to the power 10 Gauss, means using this formula we can draw that constant magnetic field lines and here constant age lines. So those are very interesting properties, means spin period and spin period derivative are the most two fundamental parameters which we can measure. But this we can do for any pulsars, means regardless of whether these pulsars are isolated or binary. But when you have a binary, that time you can measure even more parameters. Because see, if you have a binary, say you are the people in Earth, the pulsar is once here, and if the orbit is like this, pulsar is once here. So the signal takes different time to reach you. So that is why the spin period carries the information about its orbit. So by modeling this spin period, we can measure the shape and size of the orbit, means orbital period, orbital eccentricity, inclination of the orbit, and then as I said, you need general relativistic effect. So we can actually measure other parameters like change of the shape, change of the size, and because we can measure those general relativistic effects and those parameters, we can use those pulsars to test various theories of various predictions from general relativity. We can also measure masses of the pulsar and companions, because those equations of those general relativistic parameters, they contain masses. And then you can use those pulsars to detect very low frequency gravitational waves, which are not yet done, which I will tell you a little bit. But before going to that, I will just briefly mention a few other interesting application of binary pulsars to study gravitational physics. So we all know few years ago, there was first detection of gravitational waves by LIGO group, but that was the first direct detection of gravitational waves. First detection of gravitational waves was done indirectly long ago by Hulse and Taylor when the first binary pulsar was discovered. Means the pulsar which Jocelyn will discover, that was on isolated pulsar, and first binary pulsar was discovered in 75. So then if you have a binary pulsar, means two objects orbiting, they emit gravitational waves, and that gravitational waves carries energy, and that energy comes at the cost of gravitational binding energy. So that binary pulsar, it loses energy and the orbit shrinks. And if the orbit shrinks, orbital period decreases, right? So when the Hulse and Taylor are observing their pulsar and modeling, they saw that the orbital period is decreasing. And the only reason for this decrease of orbital period can be the emission of gravitational wave from the system. And here you see the plot, means those points are the data point from this binary pulsar, the rate of change of orbital period, and that line, this is the prediction of general theory of relativity if that change was only due to gravitational wave emission. So that matches very good, and that is why they got Nobel Prize in 93, And this time the PhD student Hals also got the prize. Then there are many other interesting applications. I would just briefly mention two which I like. One can be done if there is a pulsar with a black hole companion in a binary system, there will be very strong light bending effect. Means the black hole with curved spacetime around it and light will not travel in a straight path. So that can be observed, and my PhD student Jyotijjal is working on that, and here is a plot from his work. So if there was no light bending effect, if the pulsar signal was like that green curve, due to bending, you will get the pulse profile like something different. So that work is not yet finished, he is doing. There is another interesting work, study of gravitational physics came a few years ago. It was the most precise test ever done of strong equivalence principle. You know, one aspect of strong equivalence principle is that the gravitational field experienced by an object depends only on its mass, not on the constituent of the particle. So here there was a three-body system, a pulsar and a white dwarf, and there was another white dwarf outside it. And so that outer white dwarf's gravitational field on this inner white dwarf and pulsar was measured, and it was found that it just depended on the masses of the pulsar and white dwarf. Means one is neutron pulsar and another is white dwarf. That did not matter at all. And that paper, we were not involved in this work, but when this paper came out, I was very amused to see that they used my student Dhruv's code to eliminate the gravitational potential of the Milky Way galaxy. So that was actually an interesting study. But now I would, last 5-6 minutes, I will spend about what we are doing at present and very excited about. Like I mentioned about LIGO and gravitational wave, and obviously for obvious reason, we are all very excited few years ago when first detection was there, first direct detection was there. But we need to remember that was just the tip of the iceberg. What LIGO can ever detect, only the high frequency gravitational waves. And like the electromagnetic spectrum, gravitational wave is also very large spectrum. So there is high frequency gravitational waves which LIGO is detecting, and after Indian LIGO joins, they will detect more and more. Then there is low frequency gravitational waves for which we will need LISA, space-based interferometer. Then there is a very low frequency gravitational wave, and which we are trying to detect using pulsars. And there is extremely low frequency gravitational waves which cosmologists are trying to detect. So what is this very low frequency gravitational wave? They are being emitted by supermassive black holes and mergers of supermassive black holes, mergers of various galaxies in all this range, and they are coming from outside our galaxy. And in our galaxy, we have lots of pulsars, and if there is those low frequency gravitational wave, the signal of the pulsars will carry the imprint of those gravitational waves. So remember, pulsars are emitting gravitational waves, but those are high frequency. LIGO is detecting those. But we are not trying to detect the gravitational waves emitted by pulsars. We are using pulsars as our detector. We are not making any detector. Nature has given us detector. We are using a large number of pulsars to see whether we can see the imprint of very low frequency gravitational wave in their signal. And for this purpose, you need a large number of pulsar. That is why this experiment is known as International Pulsar Timing Array, because you need an array of pulsars. So there are currently 4 groups working on this. First started Australian Pulsar Timing Array, then North American Gravitational Wave Observatory, then came European Pulsar Timing Array. Then we started our Indian Pulsar Timing Array in 2015. And first few years we were associate member, And from 2021, when we proved that our data quality is as good as there, we got full membership. And here you see different countries and there be different telescope. And we have our GMRT, which I already mentioned. And here are few boring information. So this in about our Indian pulsar timing array effort. It is a multi-institutional effort. So you can see IMSC, TIFR, NCRA, RRI, IIT Hyderabad, IIT Roorkee, BITS Pilani Hyderabad campus, ISAR Bhopal, and recently Japan's Kumamoto University also joined our team. And we have members of every level of research career. You can see the statistics. There are some the senior level faculty members, postdocs, PhD students, even undergrad students in different IITs. You can find more information about us in our website. And you will see that website looks very professional. And I would thank some undergrads in IIT Roorkee who made this website for us. And I would also like to here thank IMSC and also other institutes, because like Australians, Europeans, or Americans, we don't have any dedicated funding for this experiment. But all our institutes are kindly supporting us, so we are really thankful to our parent institutes. And here we are at present. You can see our team at various ages. And here few scientific details. We are using upgraded GMRT. You see the photo of GMRT, which is located near Pune, run by NCRA, which has 30 antenna. It's 45-meter diameter. And it has a very wide frequency coverage, 300 megahertz to 1500 megahertz. And that makes us very unique. Because in this frequency range, you can divide it into various bands. And you can, each band of 200 megahertz width. And you can do simultaneous multi-band observation. And that is very unique because that enables us to measure dispersion very accurately. Dispersion measure is actually a kind of quantification of propagation delay of radio waves through interstellar medium. And we need to know it very well to model the pulse when the pulse is arriving, because that is what we are going to use to detect gravitational wave. And that made us unique. So what we have done since 2015? So because of this uniqueness, multiband observation, which is possible using GMRT only, only we can do highest precision DM measurements ever done in pulsar astronomy we could do. We made our data public recently, and our data quality is as good as international effort which started in 2014, and that is also possible only because GMRT is so precise. So I will skip these two plots. Those are just to show our data, how good is our data. So we are still continuing our observation, and more data is being pulled. We are observing and analyzing data, more and more data is being added, and all other PTS are also doing that. And the nature of this experiment is that the more data you add, the quality will become better. So we are hoping all our effort, hopefully we will detect gravitational waves, that very low frequency gravitational wave very soon, maybe in 2025 or so. So I'll stop here today, and this is what just before pandemic we organized international meeting in Pune. You see our NPTA team among the international people. So let me stop here.
Thank you, Manjari. Our last speaker for this session is Professor Krishna Madali, who was for a long time at IMSC, so we are happy to welcome him back. He's now at Ashoka. Krishna.
Thank you for the invitation for giving a talk here. I thank all my former colleagues here. We have seen an impressive talk which requires so much of infrastructure and so on. In comparison, you see that all we need is a pen and paper. So what I'm going to talk about is a simple looking statement, something called regularity of density of states. We would have studied in calculus, everyone would have studied. You take functions, you ask whether they're continuous, they have derivatives. And all I'm going to talk about is one such question. I have one function, does it have derivatives, is it continuous? That's all the talk is. But it has a origin from something else. So if you take crystalline materials with impurities, semiconductors and such are formed out of these things. You have a crystal, certain kind of impurities exist, so they conduct electrons for certain energies, they don't conduct for others, or they are perfect metals and so on. So such materials are formed by atoms, and such materials are described by random Schrodinger operators in mathematics. Mathematically, a quantum mechanical system is described by a set of states, which is a Hilbert space, and then some sulfur giant operators on them, which are supposed to be observed. This is the quantum theory that is evolved by physicists and formalized by mathematicians. So what we have is a set of states. On R3, you look at the set of square integrable functions. That means take all those functions from R3 to complex numbers whose absolute square is finite. So that is the Hilbert space. So on that Hilbert space, one has a collection of sulfur giant operators parameterized by a parameter omega. So H omega for a fixed omega is a sulfur giant operator given by the Laplacian, negative of the Laplacian, which is nothing but sum of second partial derivatives in each direction, plus some random potential which comes from, for every x, v omega x for a fixed omega is a function given by a sum like this. I'll explain to you what this is in a moment. So the operator v omega is nothing but multiplication by this function on a state f. So if f is a state, v omega f is v omega x times f of x. So that is the linear transformation. So this sum is supposed to give an energy operator that's supposed to describe the energy of the state that is responsible for its evolution, motion and such. This is the basic framework of quantum mechanics. So here what I do is R3, I'm just representing the plane. You just form unit cubes. You take a unit cube located at the point with integer coordinates n. N here means n1, n2, n3, 3 integers. So look at the integer coordinate points in R3, which is nothing but Z3. At every point, you look at a unit cube centered at it. So take such unit cubes piled up next to each other. In any one cube indexed by its center, lambda n is a unit cube centered at n. And this function chi lambda n x is the indicator function of that lambda n. That is, it is a function which is 1 on lambda n and 0 elsewhere. Look at that function multiplied by a random variable q omega of n. Omega is a random parameter. Omega comes from a probability space. So look at the collection of random variables q omega of n with the property q omega at distinct points are independent and identically distributed random variables. So in other words, this is just a sum of independent random variables multiplied by projections or multiplication by indicator functions. So that is a fancy way of telling you that a cube centered at n, you have a random variable q omega of n. At a cube centered at m, you have a random variable q omega of m. These are all independent. So in other words, each independent cube has independent random variables. So you can think of this as atoms piled up at the centers of these cubes, unit cubes, and each atom is a different type. And that's what describes the impurity. Most of them may be the same. So the independentness says it's a random system, and this totality of this collection of atoms, where you could have all kinds of impurities, is the model that is modeling the energy operator, where the parameter omega tells you that the impurities could be somewhere. I don't know where it is. For example, if I buy a copper material from one shop in T Nagar and another shop in Adyar, they may have different kind of impurities, so the omega will be different. However, in general, for all these things, the properties, generic properties should be the same. This copper wire or copper material that I buy in Adyar should conduct electricity as well as the one that I buy in T Nagar, for example. So that is the kind of statement one is looking for. So independent of the parameters, some property should be valid. Okay? So this object, this self-adjoint operator, is the one that describes the quantum mechanical system. Q omega n's are independent and identically distributed. When you say it's a random variable, it must have a distribution. So the distribution is given by a function h of x, which is its density. In other words, the probability that this random variable takes value in an interval a b is nothing but integral of h of x dx over a b. That's what it is. Okay? So that is the model. So whenever you have a self-adjoint operator, you have a spectral projection associated with it. Spectral, not only a spectral projection, there is projection valued measure associated with it. So if you don't understand it, just think of the matrix of the operator as a matrix, a Hermitian matrix, or a symmetric matrix, real symmetric matrix. It has eigenvalues. Eigenprojections are there corresponding to the eigenvalues. So the diagonal matrix that you get after diagonalizing it is precisely a fancy way of writing sum of lambda I pi, where pi are the spectral projections. So when you don't have eigenvalues but you have other kind of spectrum, you have a spectral measure, namely for any interval like minus infinity to e, you can associate a spectral orthogonal projection associated with the self-adjoint operator associated with that interval, and this will be a projection, and as a function of the interval, this is a measure, taking values and projection. Okay? So what we have is, we take the spectral projection associated with the operator corresponding to a number e. By the way, self-adjoint operators have spectrum only in the real line, not outside. And therefore, it makes sense. You take the unit cube centered at 0, look at this function that is supported there. Think of it as a projection on the Hilbert space. Multiply that with the spectral projection. You get another operator. Take the trace of this. That will give you a number. So for each e, you get a number. But then that number is a random variable because omega is there. So you simply take the average. So take the average of the trace of this operator, which is a function of omega. So for every e, you get a number. So for every e here, you get a number. Call it n of e. So as e varies, it's a function. So this function is called by physicists as the integrated density of states. Okay? Or it's called a cumulative distribution function. So it is this function that one is going to look at. By the way, this is the work that I did with my former PhD students, Dhriti Dalai and Anish Malik, if I forget to say it later. So n is the distribution function of a finite measure, and when it is absolutely continuous, we can write this function as the integral with respect to some density n of x. And this n is what is called the density of states. Okay? All right. So there is another way to describe this, which is a more intuitive way, which is how the physicists describe it. You restrict h omega to a box of size lambda L in 3 dimensions, centered at 0. And because you are restricting it to a box, it's like restricting the Laplacian to the box. So it has only eigenvalues. Take the Laplacian and in a bounded domain, if you restrict it, you only have eigenvalues. And therefore, this has only eigenvalues. And HL of omega is bounded below because the Laplacian is bounded below. Its spectrum starts at 0. And when you put a Dirichlet boundary condition, it starts at 0, but Neumann conditions, it will move up. It doesn't matter, but it's still bounded below. So these eigenvalues are bounded below. And therefore, if I count the eigenvalues below some number E, there are only finitely many eigenvalues. Because the Laplacian restricted to a box has discrete set of eigenvalues. They don't accumulate anywhere. And therefore, in any bounded interval, these are only finitely many numbers. So there are finitely many numbers. And look at these numbers and count them. Number is number of eigenvalues below E of HL of omega for a fixed L. This is a finite number. There are reasons why this behaves like the volume of the box. That's called Weil's formula, asymptotic formula. So this number is like L to the power 3 proportionate to L to the power 3, the volume of that box. And look at this object, call that NL omega V. Now this function now depends on omega. It's not independent. Okay? And secondly, a simpler way to look at it is look at the eigenvalues of HL of omega. At each eigenvalue, you put a weight 1 by L to the 3. That will give you some measure, and that is the measure one is looking at. So this is a collection of random functions with depending on L and omega for every E. So under very mild conditions on the distribution of the random variables q omega, it is known that n of E is a continuous function and NL omega V as L goes to infinity converges to n. Almost every omega. So this statement is stated as self-averaging property of these finite cumulative distribution functions by physicists. So this statement is an ergodic statement for a mathematician, but for a physicist it's called self-averaging. So hence, expectation of NL of omega V also converges to the same thing, because independent of omega it converges. So when you take averages, they converge. So n is absolutely continuous, and the density of states and IDS are related by n of E. This is the density of n, which is this relation almost every E. So here is the question. Is the density of states n of E continuous? Is it differentiable? If so, how many times? That is all the question is. Okay. By the way, it took 30 years for me to prove this. Nobody could prove it. So sometimes simple questions are hard. So the question is unsolved for random Schrodinger operators, while it was solved for Anderson model, tight bending model, which is the same model on L2 of Z3, which is an approximation to the Schrodinger operators. Instead of taking the Laplacian here, you take the adjacency operator, which is just taking the derivative on the lattice. If you write it down, you just the adjacency, and then the random variables at different sites. Now these boxes are replaced by integer points themselves, indicator functions there, they are regular orthonormal vectors there and so on. So this is a well-defined operator and in the region of the spectrum that consists only of eigenvalues. Here Ti is the right shift. So for information, in the case of a Schrodinger operator, random Schrodinger operator, the spectrum looks like from 0 to infinity it is something, and at below you have only eigenvalues. Now it's an open problem in more than 2 dimensions, more than 1 dimension, what the nature of the spectrum on the right hand side is. Nobody knows. Even in the discrete case, nobody knows what the nature of the spectrum is if the variance of H is small. So those are the major open problems in mathematical physics. So I'm going to look at only in this region, not there. Even that is an open problem for this question. So I'll be looking at this part called the closure of the set of eigenvalues of H of omega. So how long do I have? Do you have some time? 5 minutes, okay. 5 minutes is not much time. So here is the thing. I'll try to tell you the main idea. The main idea is that it is known that if you take the resolvent, if you take the current inverse of this operator after subtracting a complex number z, then this is an invertible operator. You take the inverse, multiply the projections at distinct points lambda n and lambda m, take the trace, take the absolute value for some small power, take the expectation, then that decays exponentially as n and m go to infinity, as the difference goes to infinity. This is a property in the region where the point spectrum exists. This is a fact. Okay? So our theorem is that whenever you are in this part of the spectrum where this is valid, for real z in this point spectrum, so whenever you are in the closure of set of eigenvalues, where this condition is valid, n of E has m continuous derivatives whenever H has m plus 3 continuous derivatives. Remember that earlier it was not even known whether n is continuous or not. So the idea of the proof is any positive finite measure h of x dx has what is called a Still-J transform. You take 1 over x minus z h of x dx, which is this function. It is a function of a complex number z. That's a function in the upper half plane. It has some nice properties. So for proving what I want to prove about h, all I have to do is prove some things on fs of z. So if this is differentiable in z and the derivative is uniformly bounded in imaginary z in an interval, then automatically h is differentiable in that interval. Okay? So this is what the idea that we use. And the second step that we use is that if I take a sequence an numbers and that converges to some number a, then you can write the limit a as a telescoping sum. Take a2 minus a1 plus a3 minus a2 and so on plus a1. That sum is precisely a, which is the limit of the sequence. So what we do is, this is the object we have to look at. So we write it as a telescoping sum with respect to those things that we restrict to different boxes. This is the L plus 1 box, that is L box, and so on. Write it as a telescoping sum, and then use the fact that any of these things for a fixed L has this form. It's a function of model lambda L random variables integrated over corresponding densities. Therefore, if I want to take a derivative of this whole function in E, that is simply as taking derivative on Hs by integrating by parts. Therefore, whenever H has a number of derivatives, this function for a fixed L has as many derivatives in real Z. Okay? Therefore, in the previous slide, I don't know, in the previous slide here, this function whose derivative I want to know, I'm writing it as an infinite sum of some functions for which I know that they have derivatives. Now it's a question of analysis and math and showing that there is some absolute and uniform convergence of these summands. Here, you take the absolute value of things that were inside the sum, certain uniformity and so on you have to prove, and that completes the proof, and that's what we do. Now, when I describe to you, it appears simple, but firstly, you wanted to get an idea. Secondly, you note that I have something like this, average of some quantity, but I only have a condition that the quantity that is inside the summand, only power s smaller than half, is finite and decaying exponentially. So if I have it's like saying that integral of g of x has to be bounded by integral of g of x to the power s. Should get an upper bound. That's almost impossible, right? So that is a difficulty, and how do we do it? Somehow in this context, it seems to work out. So there are lots of technical difficulties, which is why it wasn't proved for such a long time, and we managed to do it, which is one theorem I'm proud of. There's another theorem I'm proud of, which probably another time I'll talk about. Thank you. Let me say that, these were the two papers that were proved in the 85 and 88. Afterwards, nothing happened. And this is our paper. And this is the paper that gives the condition that we use on exponential decay.
Thank you, Krishna, and thanks to all the speakers. Rahul, when are we supposed to, what is the advice? When? Let's say 15 minutes. 50, okay, so it's...
talks for the day. I'm very happy to introduce Professor Debojyoti Chowdhury from Delhi University. He was a long time ago a student at IMSC, a year junior to me. He and his guide together migrated to PRL in Ahmedabad, and he completed his PhD from there. And subsequently, he was at many places before settling down at DU. Debu has worked in many areas of particle physics phenomenology and is famous for his not so wild ideas, two of which he is going to talk about today. Debu.
Thank you, Indu. Sure, thanks. Thank you, Indu, and it's fun to be back. Though I have been haunting this place in between. So I was here, what, 35 years ago, a little longer, and I see some of my teachers here, some of my fellow students. Okay, so today my talk today, since this is a mixed audience, I decided after some initial efforts that I'll not talk about what I normally work on, which is particle physics, partly because that tends to get too technical, and partly because I saw that at least two particle physicists would be speaking before me. So too much of a good thing is not good. So I'm staying away from particle physics, and I'm talking about a couple of rather crazy ideas that one had looked at. And one of those ideas had its genesis in IMSC. So I feel nice about talking it here. And I was not the initiator by any means. So I'll just mention it while I'm going about with my talk. So evolution of the universe has everything to do with gravity and matter. And just to set our notation, since this is a mixed audience, but maybe I don't need to. So gravity is, of course, a theory of geometry and energy momentum, where the variables that one uses are the metric, which for us means a measure of distance. And I've given here, I've got a pointer. Oops. Oh, which one? The top one. Okay. So what's the metric? Metric is something that gives you a notion of the distances. So for example, if I write things in the Cartesian coordinates, distance is given by dx squared plus dy squared plus dz squared, those being the infinitesimal variations. And so I would write ds squared as like this, and g mu nu is diagonal of in the 1, 1, 1. It's the same thing I write in polar coordinates. So my distance squared goes like this. And so now my metric is a different thing, beast, which can be written like a diagonal matrix once again, 1 r squared and r squared sine squared theta. This everybody knows. And again, going back to a familiar thing, if I look at a divergence of vector, and I could have looked at curl or a gradient or whatever. So divergence of vector in Cartesian coordinates is given by this, whereas in polar coordinates is this. And the idea of writing this is to just remind ourselves that when we talk about, say, a divergence of a vector or a curl of a vector, etc., it's not just the mere derivatives of the components that come in, but there are, in addition, some functions of r theta and phi, which multiply just the original guys Vr, V theta, and V phi, without the Vr theta phi being taken derivatives. Okay? So these additional functions together give me what's called a connection. So in the simplest cases, the connections are given in terms of the derivatives of the metric, but in a most generic case, it doesn't have to be so, and this is what I'm going to use a little later on. Once again, to remind ourselves of something simple, a point particle motion, So supposing a point particle is moving and it has coordinates, say qi, okay, in 3 dimensions, say x, y, z. So one defines something called a Lagrangian, which is in general is a function of q, q dot, and not so common q double dot. And the equations of motion as derived from this Lagrangian would be given by this. Okay. So, and that gives me the equation, say for example, Newton's laws would be obtained if I assume a certain Lagrangian, and this is something that everybody is familiar with. When we come to gravity, which is nothing but dynamics of the geometry, my coordinates are metric and maybe connection, and my Lagrangian is a function of the metric or the connection and their derivatives, and this together gives me Einstein's theory of gravitation, which tells me that geometry and matter are interlinked. Geometry affects the motion of matter, and the matter distribution affects geometry in turn. And this will become clearer when we look at certain solutions of Einstein's equation. For example, soon after, within a year of Einstein's writing down his equations in 1915, Schwarzschild found this solution where I've got an empty space except for a mass m, and the space-time distance, the invariant distance, is given by this function. Okay. So this immediately tells me, okay, so even if we neglect this dt square part a bit, if I just look at this, it tells me that there is this extra factor, and this tells that in the presence of matter, the shortest path looks curved. Okay, and this will, I mean, consider m to be the mass of the sun. This will also give immediately the motion of the earth around the sun, just starting with this definition as the straight line. Okay. So soon after that, in 1917, de Sitter found another solution of Einstein's equation, where one had an empty universe with something called a cosmological constant, and that led to an exponentially expanding universe. Okay. It was curiosity at that time. Okay. We'll come back to this in a little while. In another 5 years, Friedman found a third solution. Okay, there were many others. There was Reisner, Nordstrom, there was Kerr, etc. Friedman found another solution which pertained to an isotropic and homogeneous universe with arbitrary types of energy. This arbitrary types of energy includes energy due to matter, energy due to radiation, etc. Okay. So I'm not giving out these solutions. The Friedman solution I'll talk about later. But this isotropic and homogeneous universe, that is supposed to mirror the known universe at large distance scales, okay, of the order of say 20 megaparsecs. Okay. So if I sort of average out the universe at that scale, I will get an isotropic and homogeneous universe, and the Friedman equation is supposed to model that. Going back to observations, 1910s, Westo-Slipher saw that extragalactic objects seem to be moving away from us. 20s, Hubble looked at Slipher's data more carefully, made more of his observations, and found a remarkable result that objects farther away are moving away faster. So the velocity with respect to us seems to be directly proportional to the distance with respect to us, and the distance, okay. Today, we know that the relationship is not exactly linear, but that also we'll talk about later, I mean, what that relationship is. Now, if objects farther away are moving away faster, it means what? That the universe is expanding. If the universe is expanding today, I run the clock backward, then the universe must have expanded from a tiny blob, which some people call the primeval atom. Okay? And that led to a Big Bang, the idea of a Big Bang, that far back the universe was in a small place where it expanded. Now if I compress everything, say I think of the universe as a gas, I compress it, of course it will become very hot. And so in the early universe, the early universe was extremely hot, and there was an era where the ambient energy was so large that even all the hydrogen atoms, and by corollary all the atoms, were ionized. Okay? And much before that, there was an era where there was no nuclei even, because the nuclei broke. Okay? Now, this formation of nuclei, I can start from the Big Bang, work through my equations, and I get something called the Big Bang nucleosynthesis, and it reproduces the observed nuclear abundances in the universe very well. So this is considered a major success of this paradigm. So I said there was a time when the protons and electrons could not form atoms. Okay, as the universe was expanding, it cooled down, they got bound, they formed hydrogen, and we know that the hydrogen binding energy is about 13.6 electron volts, so that energy got released in photons, okay, which gave the cosmic microwave background radiation, which is a black body radiation with an excellent fit to the radiation curve. I mean, the best known black body radiation is the CMBR. So 13.6 electron volt, you can convert into kelvins, okay. So today, and it's a pretty large number, okay. It's more like 3,000 kelvins. Today, the universe has cooled down to about 2.7 Kelvin, and that is the temperature that Penzias and Wilson measured to get the black body radiation. Now, coming back to the last 30-odd years. In 1992, the Kobe mission flew, and it looked at the black body. Of course, it reconfirmed the black body spectrum, but found that there were hot and cold patches in the sky, and the degree of hotness or coldness, the relative temperature, delta T by T, was of the order of 10 to the power minus 5. Okay. And now, for the young members of the audience, you should try to find out how they could have measured 10 to the power minus 5 in black body spectrum. Subsequently, WMAP resolved this Kobe to this, and Planck, still 10 years later, got this, this kind of details in the spectrum. Okay. So the study of these small fluctuations, correlations between fluctuations, temperature correlations, and then there's polarization, etc. Okay, they lead to a measurement of various cosmological parameters. What kind of measurement? So let us look at this. So everybody here presumably has heard of something called dark energy. So if I look at the energy budget of the universe in terms of matter, by matter I include dark matter and the dark energy. Now, I look at galactic clusters. They give me this kind of a correlation between matter and dark energy content of the universe. Okay. Study of supernovae gives me this. Study of CMB gives me this, and so combined I have only this small red circle. So very, very precise. Okay. This somebody, Rohini, I think, talked about error bars being in the exponents when we were young. Today it's no longer true. And this is what we have for the energy budget today. So today we know that about 23% is dark matter, 4.6% atoms, and 72%, have I fallen silent? No, 72% in dark energy. This was not always so. If I look close to the time when, the recombination era, the proton, electron, when proton and electron recombine to give you hydrogen atom, the ratio was quite different. And this ratio was different because various components, their energy density content evolved differently. Some of them, like if it's an ultra-relativistic object, the energy density falls like 1 by the size of the universe to the power 4, whereas for non-relativistic matter, it will fall as 1 by radiation to the by size to the power 3. So the various things, and the dark energy does not fall at all with the size of the universe. So here, there was no dark energy. Here, dark energy dominates today. Okay? A lot of people also talk about this as the coincidence problem, which I don't think that's such a problem. How much time have we taken already? Okay. So now I'll just talk about some problems. Now, this plain Big Bang theory had many problems, and to cure some of those problems, okay, the problems called horizon problem, magnetic flatness problem, magnetic monopole problem, density perturbation problem, etc. And to cure many of them, one invoked a period of accelerated expansion, which is called inflation. Okay, it supposedly solves all these problems. And so, okay. However, although I had said before that the cosmological constant can lead to accelerated inflation, the cosmological constant is not enough to do this, because an accelerated expansion powered by the cosmological constant cannot be stopped. So if the cosmological constant had done that, the universe would have been accelerating madly ever since, which it did not. The accelerated expansion was only for a short time span, and then it stopped. Okay? So the traditional way is to invoke a scalar field, and then, even then, getting out of the scalar field driven inflation is not always so easy, and it needs some fine tuning. And secondly, the kind of potentials that do the job for you, at least do the job as far as cosmologists are concerned, those kind of potentials are typically hated by particle physicists for a multitude of reasons. So there is a bit of a tension. Secondly, what of pre-Big Bang? Okay? So if the universe has been expanding forever, there must have been a time when the universe was infinitesimally small, and we have no idea how to deal with that. Most of the treatment of cosmology is always classical, at best semi-classical, and for infinitesimally dense, for infinitely dense universe, we cannot use those, and all bets are off. So this, as we reach the singularity, we have no idea how to deal with things. So these two problems I would request you to remember, because this is something that I'll be addressing. Now, one more problem, observational problem. It's been much in news in the last few years. It is so-called Hubble tension. So what was the Hubble tension? So I told you about this Friedmann solution, and so Friedmann, Lemaitre, Robertson, Walker, etc., etc. It says that the metric for the universe on a large scale is given by this. Okay, there's a single function, okay, which multiplies this, and I am also assuming flat. If it's not flat, I can introduce some other factor which I don't want to at this stage. Okay, so if I have that, okay, and this factor, the sole factor, is called a scale factor because it sets the size of the universe. And once we start with this, we see that the Hubble expansion rate is not constant. Rather, it's given by this ratio, the time derivative of a divided by a. So the logarithmic, ddt of log a. Okay, and by convention, the value of the Hubble constant today is denoted as h naught. Okay, now Einstein's equation, as I said, relate geometry and energy momentum of the matter or radiation, etc. So given the radiation, matter, and maybe the dark energy, and when I say matter, I include visible and dark. So given all of this, h of t is defined. Okay. So given h of t, I can work, okay, whatever the values back then, I can work through today, and I can determine what h naught is. Okay. Starting from what Planck has seen, okay, I can get it. And once I do that, I get this value, 67.8 plus minus 0.77 kilometer per second per megaparsec. Okay. On the other hand, if I look at relatively nearby objects, supernova 1As, Cepheid variables, tip of the red giant branch, data from Hubble Space Telescope, etc., etc., I get this value. And between these two values, there is a more than 4 sigma discrepancy. Okay. Now, is 4 sigma discrepancy something to be worried about? Well, I leave that to you to judge. 4 sigma discrepancies have long been known to go away, but supposing it stays, then a reconciliation of these two objects would need changing evolution history, because this is something that we directly measure, this is something we infer, and here the history of the universe has gone in, and that would need to change. Okay. So here my first this thing starts, the wild ideas start. So non-invertible metric. So we talked about this subject called the metric, the distance measure. Okay. So what if the metric is non-invertible? Okay. For example, in a Cartesian metric, supposing the Cartesian metric were like this, which means ds squared does not get any contribution from the x direction, it gets contribution only from the y direction and z direction. Okay. X separation has no bearing on distance. Okay. So that is okay. Now if this is so, then doing my usual formulation of gravity becomes a little tricky, because those of you who remember, to derive the gravity, to write down the gravity Lagrangian in the usual formulation, so-called Einstein-Hilbert formulation, I need to consider not only the metric and its derivative, but also the invert, the inverse of the metric, okay, to get a scalar object. So that is why there is a problem. Apart from that, there is something called a Palatini formulation, where both metric and connections are used as independent variables, hence my original this thing of the connection. Now, for invertible metric, both of these guys are equivalent, both formulations are equivalent, and it can be shown rigorously. For non-invertible metric, they are not, and Ramesh Kaul and Sandeepan Sengupta here did a lot of work on this, and they are the ones who introduced me to this idea, and so my hat tip to them. Okay. And they found several very interesting features in this. Okay. I'm not going to be talking about what Ramesh and Sandeepan did, because they must have given talks here. So, but on the other hand, metric, okay, you would say that a non-invertible metric seems ridiculous, because we know from our experience that metric is invertible. Okay, it's 1, 1, 1, the distance, at least in Cartesian coordinates. So we have a different take. Okay, just, this is a speculative bet. Supposing the world is in 5 dimensions, okay, just for the heck of it, and we are confined to 4 dimensions, okay, and the 5D metric is assumed to be rank 4, okay. So 4 eigenvalues which are non-zero, and 1 eigenvalue which is 0, okay. I go ahead with this, And with the simplest construction, I can get the so-called late time acceleration that we see today, and for which one has to invoke a very tiny cosmological constant which people do not like. Okay? But let's be more ambitious. Okay? Since the metric is non-invertible, we use the Palatini formulation. Technically, you should use the field binds, etc. Let's not go into that. But I write this Lagrangian, which is a 5-dimensional object, plus I can write a 4-dimensional contribution to the Lagrangian, which is confined to only this 4-dimensional hypersurface that we know of. Okay? I won't go into the maths, but it gives me such an expression. This Hubble constant, or Hubble expansion rate, divided by h naught square, which is today's value, I get in terms of these objects. Okay? It's a complicated looking expression. So where this omega m naught and omega gamma naught are matter and radiation energy today. Okay? And these two are couple of parameters that appear in the theory. Okay? Now once I get this, I can test it against supernova data and demand consistency with CMBR. Assume that I play this game. What do I get? Okay? So we did a Markov chain Monte Carlo, and there we get these values. Okay? So this is where I assume there's no radiation, and here assume a small amount of radiation that is consistent with what we know of the world today. And well, it's not surprising that nothing really depends on this. Okay? These two values are virtually the same. Okay? Now, note one thing, that this value of h naught is 72 plus minus this, which is absolutely consistent with the near field measurement. Okay? So one seems able to reproduce the near field measurement and or cure the, so this is a 2-dimensional this thing of the same thing, but since I'm running out of time, one can cure Hubble tension. It requires slightly less dark matter, that's not than the conventional idea, so that's not a problem. Dark energy is roughly same, but more importantly, okay, look at this parameter B, okay, which is a combination of these other parameters. Now the B value, you see its central value is 0.036, and on the negative side, the error is larger than the central value, so which means B can be negative within 1 sigma. Now what if B is negative? B is negative means the argument of the square root turns negative, which I cannot have. Okay? When will the argument of the square root turns negative? When this guy becomes bigger in magnitude than the rest. And when will that happen? When A becomes small. Okay? So which means that A cannot become very, very small. Okay? If I take this idea seriously, then if I have a slightly negative value for A, it can give me a minimal size of the universe. So the singularity problem would be avoided. Similarly, a maximal size of the universe also comes into being. Okay? It's a toy model. Okay? So should I believe in it? I'm not saying that one should, but it's curious. Now I have only 5 minutes. Okay. So wild idea 2. Okay? So wild idea 2, if I have delayed interactions. So now delayed interactions appear in many biological systems. Gautam here is an expert, and so are many others. Okay? So what if I try to apply this idea to cosmology, to gravity? Where do I get delayed interactions? It can presumably come from non-local interactions which could have their origin in string theory or loop quantum gravity or spin form. Anything one doesn't know, one ascribes to string theory. Okay. So we said that there's a, at large scales, we have this so-called Friedmann equation, which is this. The Hubble expansion squared is 1/3 rho t, where rho is the total energy density. Adiabatic expansion of the universe, along with first law of thermodynamics, gives me this, where P is the total pressure density. Together I get this, which I can rewrite like this. Okay? And this tells me that for an accelerated expansion to occur, I need rho plus 3p to be less than 0. Okay? That is not possible with any form of known matter or radiation. Okay? So usually one gets that by invoking this inflation, where I have a scalar field that rolls on a sufficiently flat potential, etc. So that's an ad hoc way of doing this thing, because this guy does not play a role in anything else that we can directly measure. Suppose we say, it's a very phenomenological answer, no theoretical mooring. Supposing we say that this A dot by A squared is proportional to rho at a past time. Not today, rho, but at past time. Now, terrestrial experiments, the best experiments that we have done, okay, says that this delay has to be less than 10 to the power minus 27 seconds or all. Okay. There is a long way to go before we reach the Planck length, okay, where gravity becomes strong, okay, 16 orders of magnitude. So if we have a small tau, small delay, I should not expect any effect in late time development. So I start with this, and I still do this adiabatic and first law of thermodynamics. I get my equation to be this, which has to be contrasted with the standard equation. Okay? No big deal there. First year, okay. Now, what about the matter? I take the simplistic attitude that all cosmologists take. I say matter is simple, and it's of the form where P, the pressure, is some constant times rho density, and then first law of thermodynamics tells me that rho goes like this, and where these three are various forms of W for various kinds of objects. Fine. So now, I'm talking about the equation with delay, so I cannot use just one initial condition. I have to give initial condition over the entire delay period. So I do that. Okay? Now this is arbitrary. Okay? I assume that A at this epoch went as some function which is t to the power alpha. Okay? Now this function is not derivable within the bottle. Okay? I could have chosen, can I take 2 minutes extra? Just 2. Okay? I could have chosen other forms. Now if alpha is less than 1, the universe is decelerating initially with alpha less than 0 implying a collapse. Once I do this, once I solve this, in the first epoch, I get this, okay? And lo and behold, I get inflation, okay? Scale h of t, which is constant, so A going exponentially is the inflation, okay? So what do I find? I find a phase of fast growth exists for a wide range of A, and throughout inflation, rho plus 3p is greater than 0 in contrast to all known inflation models. Okay? Okay? The condition of inflation actually now reduces to this. Okay? The rate of growth is determined by initial matter density rho naught. Now, normally, energy density pulls you back. Here, we have the opposite thing, that instead of slowing down the expansion, the larger energy density throws you out with more violence. Okay? So duration of the inflationary growth phase is only about this, and the universe quickly goes to a non-exponential expansion rate, okay, after this period. So, the graceful exit comes out automatically. How much inflation? Well, that depends on what kind of parameters I choose. Okay. So, this upper set, okay, in the tau rho alpha plane, the upper set is about 70 e-folds, and we need only 65 e-folds. The lower one is about 700 e-folds, okay, 10 times larger. Okay. Dependence on W is small, as we saw, seen. Okay. So, as I said, the faster the universe was collapsing, the faster it rebounds back. To get an acceptable amount of inflation, I need tau to be order of 10 to the 2 to 10 to the 3 T Planck, which is reminiscent of the usual inflaton scale, being about 3 times 10 to the power 3 times below the Planck. Okay. So, since Indu is threatening me, let me stop here. Okay. Sorry to have taken too long.
Very nice 2 ideas. Yeah. Yes, yes. You have to stay there and get your memento.
That is the first time I have got anything for giving a talk.
What about the stuff you got under the table?
It's always the first time in life.
Yes. And I'm very happy to do that. Not at all brilliant techniques. So I now request the remaining speakers to stick to time. The next talk, no, you're not, sorry. Next talk is by Manas Mandal, who will talk about the cohomology of generalized Dole spaces. I'll give you a warning at 10 minutes, so you'll have 5 minutes more.
Hello. So, first of all, I wish you Happy New Year, and today I will talk about cohomology of generalized Dole spaces. So, mainly I aim to explain you an example of the paper of joint work with Parmesar and Sankaran. So, that will be only last 2 slides. I won't go too much in the details. So the main keywords in the title, as you have seen, is cohomology and generalized Dole spaces. So first we will have an idea of cohomology, and in cohomology there is a very nice symmetry in the cohomology groups that we will see using Poincare duality, and another keyword generalized Dole space that we will see, and we will see another example also, that is a sphere bundle, and then we will try to understand the example there. So the basic thing in algebraic topology is that first you take a topological space and then we try to attach a algebraic structure to it. So cohomology is also part of algebraic topology, and here also we will do the same thing. First you take a topological space X, and then we attach a sequence of abelian groups. We denote it by H0, H1, H2 in that way. And then if you take all of them and make direct sum, so there we will have a multiplication with cup product, and that makes this H star in the direct sum of all the abelian groups a ring structure. And so why do we want this actually, why do we try to attach these algebraic structures to topological spaces? So sometimes studying algebraic topological spaces directly is hard. So even like two topological spaces are different or not. I mean, topological spaces are like somewhat whatever we see in real life, like chair, table, all these things are topological spaces. So everything, almost everything can be considered topological spaces. And so those things which we see, that we can easily distinguish that they are equal or not. But like in higher dimension, we don't see them. But there are also topological spaces, and we want to check that they are equal or not, in some sense that one can be deformed from one to another or not, continuous way, like without cutting and pasting. So that's why we need these algebraic invariants. So if for the like equivalent topological spaces, the attached invariants will be same. So if the attached invariants, algebraic invariants are different, then the topological must have been different. And here in this idea of cohomology, there is a thing called coefficient ring R. This is very similar. When you define a vector space, you will have a scalar field, right? So that is very similar to that one only. And once you have this coefficient ring, we denote this HIXR. This is the ith cohomology of X in coefficient ring R. So this is in red color. So I request you to remember this notation. I will be using it. So now let's see an example for that. So this is the space you see, it's a torus, we call it torus, and it is actually product of two circles. So you can see that, like if you take any point in the horizontal blue, for every point there you have a vertical circle in the red direction. That's why you can visualize that this is product of two circles. And the cohomologies of these things are presented here, meaning this H0 represents the number of component of these topological spaces. So as you can see that this is one component only. Like if we would have taken 2 points, we would have 2 components, but it is a connected thing. One from one point to another, one can go easily within the space, within this, staying in this torus. So that is connectedness. So this means it is connected means we have only one. You see here. So the coefficient ring is mod 2 here. We can take anything, like we can take integer, set up the group of integers, we can take anything which is commutative ring with identity. So here we have taken this Z mod 2 group, sorry, Z mod 2 ring. And this H1 has 2 components, Z2, another component Z2. Red Z2 represented by the submanifolds, meaning these circles, all the vertical circles represent this component. And you see that any component, any 2 vertical circles in the red direction, that can be transformed from one to another without tearing it. That means they represent the same element in the cohomology class. So that's why it is like class of A, not by A. Similarly, for the B, if you take any 2 horizontal circles, one can be transformed from one horizontal circle to another. And then the two-dimensional cohomology class will be represented by this whole thing. This is, and there is no other two-dimensional cohomology class. And all other higher dimensional cohomology will be 0, that one can show. And in this commutative ring, this cup product, the ring structure, for the ring structure, the multiplication is commutative. And one can show this one also, like this. And if you choose a point, any point which represents a component of the space, this is the identity in the multiplicative structure. And if you take this vertical circle, 2 copies of this vertical circle, okay, so that, okay, if you take a vertical circle and you multiply with itself, that will be 0. I will show an explanation for in the later slides. So this means this A times A is 0, B times B is 0, and A times B, one can show that it is the whole torus. And and if you multiply torus with the cup product, it becomes 0. So now I will talk about the symmetry in the cohomology groups. So if you have a closed n-dimensional manifold, closed meaning it is compact and without boundary, and one can show that for such manifolds one can have only surviving cohomology groups starting from H0 to Hn. Afterwards all cohomology groups will be 0. So these are only interesting cohomology groups, other cohomology groups are 0. And there are isomorphism, like all the semicircles are isomorphism, you can see. The topmost is isomorphic to the bottommost, the second top is isomorphic to second bottom. In that way, this Hi is isomorphic to Hn minus I. This is a very particular statement of Poincare duality. It has very general statements also that I don't want to explain here. And so this Poincare duality, so these isomorphisms are Poincare duality isomorphisms. So if you take an element here, name it X, and the image under this isomorphism, the Poincare dual of X which stays here, we denote it by X star. Now assume 2 cohomology classes. So as you have seen in the last example in the torus, there are classes which was represented by submanifold, one-dimensional submanifold which were circles. So we have seen that cohomology classes can be represented by submanifolds. So now assume that we have 2 cohomology classes represented by 2 submanifolds M and N. Then if you take the Poincare duals of them and if you multiply them, this M star meaning the Poincare dual of M, Poincare dual of N, and if you multiply it, it will be the Poincare dual of their intersection, the intersection of those submanifolds. So provided this intersection has to be transversal, means it has to be a very nice intersection, like X. So in that way, yes, 5 minutes left, okay. So now I will talk about generalized Dole space. So it is, so you take a topological space and you take an involution there, meaning if you compose it twice, it will become identity map on S. If you can think of it, if you take S to be a circle and if you rotate it 180 degree, then this if alpha is 180 degree rotation, then it is a involution, because if you do it twice, you will get back to your previous position. And you can think that this has no fixed point, because every point is moved to its opposite point or 180 degree rotated point. And if you take another topological space X and an involution with fixed point possibly, there has to be a fixed point of course, then you can construct this S cross X and alpha cross beta. So I will give an explanation for that, like what is this map actually. Basically alpha is acting on S, it is understood I think. So this has no fixed point. Then you identify, so in S cross X, you identify those points, S comma X and alpha S comma beta X. Then S cross, then the quotient space of S cross X is called generalized Dole space. So the classical case is when S was Sm, the sphere of dimension m, and X was Cpn, the complex projective space, and the involutions were antipodal map and it is conjugation, complex conjugation. So we denote the generalized Dole space made out of S and X by PSX. So you see in this example, so if I take S to be a circle and X to be a circle, and here this is 180-degree rotation, meaning x comma y goes to minus x comma minus y, and here you take the reflection with respect to x-axis. Then this alpha cross beta takes one point to the opposite side and reflected with respect to this green line. So this is alpha cross beta is doing, taking every point to its opposite side and taking the reflection with respect to green line. Then you, so in this torus, you identify all those pairs, like think of these two points as one point, then you will have some space that is a generalized Dole space, which is denoted by this P_S_1 S1, and one can show that this is Klein's bottle, meaning if you identify those points, you will get this Klein's bottle. So similarly, we had S1, now we have Sm, and similar map like going to x going to minus x, and here reflection with respect to the last coordinate. Then we will have this PSM PSN, which we denote in short by PMN. 1 minute. Okay. So then we have this ring structure. So then we can compute the ring structure for that. That is this. So P11, as we saw, it was Klein's bottle, and it can be shown that it is connected sum of two copies of two-dimensional real projective spaces. So similarly, one can show this one, like PM1, it is RPM plus 1 connected some RPM plus 1, and one can show that the ring structure is this one. And so I don't have time now, but yeah, so for n greater than 1 cases, we have the ring structure is this one, where A is the ring structure for RPM. And this is an example which this is just done in more general case in our paper here. And here we have computed the ring structures for generalized Dole spaces in much more generality. And this is the work done with Parmeshwar and Sankaran. Yes. Okay. Thank you.
Thank you, Manas, for sticking to time so well. The next talk will be by Hitesh Garg. I forgot to mention that Manas is from IMSC, so is Hitesh Garg, who will talk on the conformal phase diagram of neutral polymers and attractive crowders. I think it will take a minute to change over the laptops.
Next and back.
Hi all. Sure. Thank you, organizer, for giving me opportunity to present my recently archived work with my guide Satyavani Vempalla and co-guide R. Rajesh. So title of my talk will be the conformational phase diagram of neutral polymers in the presence of attractive Crowder. I'll be defining these terms along the talk. So initially, like what is polymer and why to study polymer? So polymer we might all have studied in our class 12th, that some atom or the molecule which repeat itself to form a long chain, which we call either polymer or macromolecule. Why we study? Because polymer is ubiquitous in nature. It is present all around us, like in material science, in living nature, in our body, everywhere polymer is present. So it is really important to study about characteristic of polymers. So what I am studying is the conformation of the polymer under various conditions like temperature, various interactions, various pH values and all. So in this study, mostly we have studied about the conformation in different interaction. I'll be discussing that. So polymer physics can be done in three ways: experimental way, simulation, or the analytical. What we are doing is simulation. So I'm just briefly explaining the algorithm and the technique which I am using. So we are using molecular dynamics technique, which has very simple, like equation of motion we are solving here. So for that, we need some initial position and initial velocity to be given for the particles. From that, after giving initial position and the velocity, we need to give them some interaction through which they interact with each other. So here I'm talking about the neutral polymer. So they just will talk to each other through algebraic. This is van der Waals potential having this mathematical form for epsilon, and where epsilon is kind of strength of the potential and sigma acting as a size of the particle. After giving potential, we can calculate force and the acceleration, and from that we can calculate final position and final velocity through some algorithm. We are using like velocity-Vallée algorithm. So this from that, like we will evolve all the trajectory and we'll get final position and the final velocity of the particles. So what I am studying is conformation of the polymer, that what kind of shape and the size polymer will take under different interaction of with the different particles or different solvent or Crowder. For that, I just briefly want to discuss what is the general trend in polymer physics, like how polymer conformation take place in different solvent condition. Solvent is something you can call that in which solute is being dissolved. So here you can see there is a polymer consists of monomer, which I am saying M, which is connecting to each other through some harmonic bond, which is being dissolved or submerged into some box containing solvent particle or Crowder particle. I will be using interchangeably these terms, solvent or Crowder, which means the same actually. See, so here there are some notation that it could be good solvent. Solvent can be characterized into three different categories. That one can be good solvent, poor solvent, or theta solvent, or the ideal solvent. Good solvent is something in which polymer won't like to dissolve into, whereas in the poor solvent it doesn't want to dissolve into, and the theta is in between condition. So what is the expectation is good solvent, polymer will be in more or less in the extended kind of form, whereas in poor solvent it will be kind of collapsed form, and theta will be in between form. What question we are addressing is, what is the general conformational phase diagram in epsilon mm, epsilon mc phase space, and how the phase line are affected by the various interaction and the densities. So since I've talked the interaction of the particles between monomer and the monomer Crowder, so I'm saying solvent as the Crowder here. You can see here the epsilon that I'm talking about, epsilon mm and epsilon mc, is the strength of the potential. Here, strength of the potential. So since there are two kind of particle, monomer and the Crowder, so there can be three interaction. Between monomer, between monomer Crowder, between Crowder and Crowder. Monomer I'm saying epsilon mm, and monomer Crowder is epsilon mc. So what is general expectation or the intuition is, if epsilon mm is greater than epsilon mc, that means monomer attraction is greater than monomer Crowder attraction, which means monomer wants to attract more with the Crowder, hence will form a collapse kind of form, which you can see here in the VMD image. If the second case, if epsilon mc is greater than epsilon mm, that means monomer has more attraction with the Crowders compared to monomer, and hence they will form some kind of extended kind of form, which you can see here also. And the third one is in intermediate kind of stuff, when the interaction is kind of comparable to each other or the equal. So again, the question we are asking is what will be the phase diagram, conformational phase diagram, whether the collapsed form or the extended form, when we vary these interaction epsilon mm and epsilon mc. So this is our simulations result. So what we did is we plotted a radius of gyration with epsilon mc on the x-axis and with the different epsilon mm shown in different colors. Radius of gyration is basically a measure of extent of the polymer. If polymer is in the extended form, we will expect Rg to be high, and if Rg is low, that means polymer is in the collapsed form. This is just a measure of extension of the polymer. From that, from these curves, we got a phase diagram. We defined some inflection point on these curves, and from that we are saying them to be transition point. From that, we came up with this kind of phase diagram. So black curve is the phase lines, and there are 3 phases we came up with: E, Ci, and Cb. So I'll explain them briefly. So if we look at the red curve, that epsilon mm to be very weak and epsilon mc to be also very weak, what we would expect is it in the kind of theta or the extended kind of form. That phase we are saying to be E, that extended phase due to weak interaction, E phase that been shown in the red dots, and you can see here also it's in the extended form. When we sit here on epsilon mc to be 0.1 and we go along this way and go along y-axis from epsilon mm to 0.1 to 1, what we will expect is, since the attraction between monomer is increasing, that means chain should go from extended to collapsed form, which is what is happening if I'm showing here. If we go from red here, that is epsilon mm small, to epsilon mm high value, we are going to a second phase that's shown by yellow dots, and this phase we are calling Ci phase, that is collapse phase due to intrapolymer interaction. This was very intuitive, that as monomer attraction is increased, so they will form collapse kind of behavior. What was non-intuitive was, if we sit on again this red curve and here is this value, as we increase epsilon mc, one would expect that the attraction between monomer and the crowd is now increasing, that the value of Rg or the form of the polymer should be in the extension, and Rg value either should remain like this or it should increase. But what was happening was this Rg value was getting decreased as we were increasing epsilon mc, and this is happening because the Crowder particle was acting as a kind of glue or as a bridge between 2 non-neighbor monomers and making the chain to collapse. So this phase we were calling Cb, and this Cb phase is collapse phase due to bridging interaction. It has nothing to do with the monomer interaction. It's totally depending on the Crowder interaction, monomer-Crowder interaction. So this phase we are calling Cb phase. So these are the three phases. As we go from E or Ci, as we increase epsilon mc, we are entering into the other phase, Cb phase. Since I'm calling the collapse phase to different phases, one is Ci and the Cb, how can we claim that these 2 phases are the different? For that, what we did is we make an analysis. We plotted something called G of R, that is pair correlation function between monomer and monomer Crowders, which will give us how the kind of Crowder are arranged themselves along the chain or around the chain. So you can see here, the black curve is for Ci phase, the one with the intrapolymer attraction, the collapse due to intrapolymer attraction. We are seeing there is a peak here. That means if you sit on a monomer and see around that, you will see the nearest neighbor to be another monomer. Whereas in the Cb phase, that blue curve, you are seeing the peak is absent. That means if you sit on a monomer and look around the neighbor, you will not see any another monomer. What will you see? You will see red peak here, that is between monomer and the Crowder. What does it mean? That if you sit on a monomer, you will see on the neighbor a Crowder, not a monomer. So like I'm claiming here, or it's been claimed that this is the Cb phase is totally driven by the Crowder, and the Crowder are coming inside of the chain, whereas in the Ci phase, there was no Crowder inside the chain. So these 2 are the different collapse state, is the take-home message from this slide. From this, I just want to mention that Cb phase is totally independent of epsilon mm. They are coinciding with each other. That means it's totally driven by the monomer Crowder interactions. Okay, so now just I want to, this was the work conclusion. Now I just want to go what in future we are trying to implement. So there is a something called depletion interaction, which was discovered by Asakara Osaka in 1953, and then later in 1980s it was very popularized. So, a very basic concept. If we take two types of particle, type A and type B particle, and we keep increasing type B particles density, what will happen? Type A will come closer and form a phase separation from the whole solution. The attraction arises because of the increment of the density of the type B particle is known as depletion interaction. But in the literature, basically, when the depletion interaction is being discussed, mostly the interaction between them is totally hardcore repulsion and all. But since we are studying attractive interaction between the particles, what we got is, so I'm just talking about the Crowder effect now, since I have not talked about Crowder epsilon cc, I just talked about epsilon mm and epsilon mc. So if I take some epsilon cc value, 0.3, and as the density is being increased, I'm seeing the RG values decrease, which was very intuitive that this depletion effect is being playing a role, that as you increase the density, chain will form a collapse form. But what was very interesting was, as I tune the value of epsilon cc to 1, the collapse is more prominent, which is very interesting, that without the depletion is basically seen as a repulsive interaction between the Crowder and the monomers. But here I'm saying if we tune the Crowder interaction, we can also see collapse behavior without even changing epsilon mm, or without any change in interaction between monomer and Crowders. So for that, now we are trying to implement that this result into some only Crowder only system. So if I take Crowder only system, meaning only Crowders are there in the box or container, and as I increase epsilon cc and density and all, we can get 3 phases. So like just van der Waals particles, you can get 3 phases. One is homogeneous phase, the other is coexistence phase, where 2 phases exist together, and third is totally droplet phase, all the particle will just form a droplet. So generally what happens is there is some, okay, so the next. So this is the rough phase diagram which we got here. Work is still pending, so I'm just showing this in a rough manner, that there are 3 phases I'm showing here, and as we sit on a particular density and increase the y-axis 1 by epsilon cc, you can map it with the temperature of the system. So as we increase the temperature, you will go from like a droplet phase to coexistence to homogeneous phase. So what is happening? There is some critical value of the transition, then below the critical value of the temperature and the density, you can't see 2 phases together. I mean, if the temperature of the system is too high, you will not see that the homogeneous, whatever density you take, you will not see the homogeneous phase will go to either coexistence phase or droplet phase. What we are trying is, we want to put a polymer inside that kind of system and see whether the introduction of polymer decrease this critical value, like what will be the effect of, we don't know the decrement or the increment, we just want to see what will be the effect of the introduction of the polymer in these critical values of this phase diagram. To scale phase diagram for various phases and introducing polymer chain and changing density interaction will affect the phase is what we are trying now. Thank you.
Thanks, Hitesh, for sticking to time. Now we'll have Pavitra S. Also from IMSC, she'll be talking about the evolutionary trajectories of Candida auris through genome rearrangements.
Hello. Yeah, thank you. Good evening, everyone. I am S. Pavitra. I work with Rahul Siddharthan from the computational biology group of math science. And the work that I'm going to present today was done in collaboration with Professor Kaustav Sanyal. He has a nice mycology lab in GNCSR. So I have picked up one organism that from the plethora of the ones that he works on. So Candida auris. This is the organism that I'll be talking about today. What is special about Candida auris? It's a fungus, and not just a fungus, it's a human pathogen fungus. So why should we be interested in this? Because, okay, so the plate picture that you see there is a colony formation of Candida auris. And here you see the classification of Candida auris, but rest apart, Candida auris is interesting because among all the species of Candida, this guy has been discovered fairly recently. Recently means a decade back in 2009 from the ear canal of a patient, a Japanese patient. And surprisingly, this particular Candida auris is seen to infect people who are immunocompromised. So it causes something called nosocomial outbreaks. That means hospital-related. I mean, people who have a compromised immune system, they are susceptible to Candida auris. And apart from these the infections that Candida auris cause are really difficult to treat. Why? Because broadly there are 3 classes of antifungal drugs, and this Candida auris can have a nice resistance to all the 3 major classes of antifungal drug. So that's why it's multi-drug resistant human fungal pathogen. It is tolerant to sterilization agents, and it can also survive elevated temperatures. Okay, so as I said, it was first discovered in 2009. Well, since then, there have been simultaneous outbreaks at isolated geographical locations across the world. So, so the question that we tried to address was, what could drive this rapid emergence? So, generally, when these microorganisms, they develop some sort of resistance. So resistance, there is a lot of changes that happen at the level of chromosomes. That is karyotypic alterations that goes around. So we probably thought that, okay, so this was the approach for this study. And we looked at, so centromere is something that I would like to give an introduction to. So centromeres are a functional part of chromosomes. So in this picture you see a chromosome. So the general picture that comes to our mind for a chromosome is that X-shaped, and the constriction that you see, that's what is called as a centromere. So during cell division and all, it is the last point of contact between 2 sister chromatids. So why centromere I'm talking about here is because the previous studies in the related fungal studies has revealed that regions in and around the centromeres happen to be the hotspots for karyotypic alterations. So yes, so we focused on centromeres. Now within yeast, within yeast species, Saccharomyces cerevisiae is the most popular one, and we all know about it. So there is a range of the structure range. So centromere doesn't come in one shape. It is sort of comes in different forms. So in Saccharomyces cerevisiae, or the baker's yeast, it is a very small 125 base pairs long centromere, and hence called a point centromere. In other, so here C means Candida. So in other Candida species, they have non-point centromeres or an extended centromeres, and hence called regional centromeres. But they have other distinct features that set them apart. Yeah. So the ones that we are interested is the last one. So here PhD means pericentromeric heterochromatin deficiency, deficient centromere. Sorry for the big word, but it means that a non-active region which kind of surrounds the centromere, that is deficient in Candida auris, which is not seen in otherwise the related species. So just wanted to point out this. Right. So the first step towards this was identification of centromeres in the Candida auris. This is an experimental work, and this was done in Corsus's lab. The centromeres were identified through various experimental methods. Not getting into the details, but they conform to the usual picture of nuclear localization of the centromeres, punctate formation in the gel, in the picture, immunofluorescence picture that is shown there. And the other features, yeah, okay, sorry. Yeah, this one, yeah, right. So this is, so we have nuclear periphery localization of centromere. So in centromeres, there is this different protein or variant protein of histone, which is H3 variant. This again it's called CENPA. So using this protein, basically we go after this protein to track where the centromeres are. So basically we get the identification of centromeres, and we were able to tell that they were small, regional, they were rich in CENP as what is expected it to be, and they have a GC poor region, and as is earlier told, it lacks in that inactive zone, peripheral zone of that centromere, and it doesn't have any repeats in that particular stretch of centromere. So centromeres come out as a very unique sequences, and yeah, that's about it. So, okay, so as I told that there were four different clades, that is basically the simultaneous emergence across different geographical locations in the world. So there were four major clades or groups of this Candida auris species, and so the approach was to look at how these chromosomal rearrangements or the karyotypic alterations happen across the clades, and then we try to look at Candida auris, nearby species, and Candida auris and a little bit far apart species. So these are the levels at which we try to look at how the alterations have happened. So this is across the clades, and these are the regions which are just nearby to the centromeres, and all of them are consistently aligned. There are no arrangements within the centromeric regions as such. And when we look chromosome versus chromosome across the clades, clade 1, clade 2, clade 3, they did not show much chromosomal rearrangements. Yes, clade 3 and clade 1 had some translocations, but the most striking or interesting thing that was that from clade 2. Clade 2 is the, so in clade 2, we had 7 chromosomal rearrangements as compared to clade 4. And out of these, 5 chromosomal rearrangements, and out of these 3 of 5 were in and around the region of centromeres. So, yeah. So clade 2 kind of is different when compared to the rest of the clades. Right, and then, so that was across the clades. Now, there is a complex called hemilionite complex. Basically, it's a set of 3 Candida species, Candida dubus, hemilionite, pseudohemilionite, and hemilionite. These were the 3 that we compared our alterations with. And I'd like for you to take a note on Candida lusitania, which we will come across in the later part of this slide. Yeah, so these are called, so this is a centennial analysis. What I mean by centennial analysis is basically mapping the regions of chromosomes of one species with the other. So here it's clade 1, clade 2, clade 3 with the hemilionite complex. So here we see that there are not much chromosomal rearrangements when you have clade 1, clade 3, clade 4 against one of these hemilionite complex. But clade 2, it has several breakpoints happening and lot of rearrangements happening even when it's across the, in this dubus hemilionite species. Yes. So Candida lusitania, so Candida lusitania is again, it's yet far apart from Candida auris as compared to the hemilionite complex. So here we again did the same centennial analysis for this organism. And this one was completely disarranged. So, but what we could get out of it was, focusing on again the centromeric regions was, sorry, I forgot to mention, but this lusitania has 8 chromosomes. Our auris has 7 chromosomes. Now, during the evolutionary timeline, there has been some sort of inactivation or something that has happened which has led to the reduction of 1 chromosome. So, keeping that in note, it was found that 2 chromosomes from lusitania, that is the one which has 8 chromosomes, they were mapping, the centromeres from those 2 chromosomes were mapping to 1 chromosome in auris, which is the middle one. So, they were mapping to chromosome 4, and it happens that only one of them end up being a functional centromere, and the other one, which is chromosome 8, the centromere from the chromosome 8, it maps, but then it is not functional. That particular region has somehow undergone sequence reduction. Sequence reduction in the sense the GC poor part that I had told earlier, that has reduced. So this was one point that led to say that there has been an event of inactivation of 1 chromosome if you look from lusitania to auris. And apart from this, there are events of duplications and duplications. Again, coming back to clade 2 of Candida auris, it is proposed that it might have followed a very unique evolutionary trajectory, given that it has so many absolutely different rearrangements happening within them. So, this is a proposed evolutionary path that Candida auris might have come traced. So, there could have been a common ancestor of the lusitania and another species which is from the same umbrella. And this hemilionite complex and Candida auris, these might have had a different common ancestor. Like clade 2 might have just diverged out. And from these, because there is also an event of chromosomal terminal translocation, meaning which that there's another event of rearrangement which sets apart this. So, yeah, so that's about it. So this was about the rearrangements that were happening around the Candida auris organism. So this quite recently, as I said, the clades were distinguished on the basis of the geographical places that they were found in. But recent reports have also reported that from the same location, you are getting organisms that that are from two different clades. For example, the East Asian clade, now you have organisms that correspond to clade 3 as well as clade 1. So geographical location based clade typing might not be an efficient way of grouping the new strains which are found. So there are many efforts being taken to classify the strains into different clades. Here what we've tried to do is look at some specific genome sequences in the clades that we had known previously, like from before the mixing event has happened. And we have tried to look at unique genome sequences that could correspond to only that particular clade. So we try to, so this is a schematic of what of the process. So pairwise alignment of the strains belonging to, okay. Yeah. So basically focusing on the misaligned regions or the breakpoints, we were able to get the unique regions, and on the basis of that primers were designed, and basically we ended up with having a very rapid experimental setup with the aid of some bioinformatics tools that could actually classify these strains into different clades. Yes. So it was validated and it was working fine and good. Yes, so summarizing the work, we had, so centromeres could be the focus of research if we were to look at for other strains that are coming up. And clade 2 is again is something that we could focus on, given that it undergoes a lot of rapid chromosomal rearrangements. And yes, that's it. These are the like work. These are the papers that correspond to the work that I just presented. And yeah, thank you.
Thank you, Pavitra. We now go to the last talk of the session by Ajay Subbarayan. He'll talk about what appears to drive complex cellular decisions. I'll give you a warning when there's 5 minutes. It's nice, don't worry.
Hello. PPT. Next. Okay. Very good evening to all. Firstly, I would like to thank the organizing committee for giving me the opportunity to present my work in front of such an esteemed audience. So the topic of my presentation is simple regulatory logic appears to drive complex cellular decisions. So over the next few slides, I'll be explaining how I reach this conclusion. Right. So the first thing is that a cell takes in many inputs, processes it through its signaling and gene regulatory networks, and this eventually leads to a variety of outputs which range from cellular differentiation, cell growth, and apoptosis, to name a few of them. Now the question is, how do you mathematically model such a system? So the mathematical framework which I would be focusing on is known as the Boolean modeling framework. So I would be explaining what a Boolean model is in this following slide using an example of cell differentiation in pancreatic cells. So the first component of a Boolean network is the network structure, where each of these nodes in this network represents a gene, and the incoming edges to any particular gene represents the regulators of that gene. So each gene takes two expression states in a Boolean network, either 0 or 1, so the gene is either on or off. And so if you take the entire network, you would have, you can represent it as a binary vector, which essentially corresponds to the gene expression pattern of the system. Associated also with each of these nodes is a Boolean expression. So what does the Boolean expression do? It's the sort of the combinatorial regulatory logic at each node, which essentially tells that particular node how to evolve in time. So if you take PTF1A at time t plus 1 is a Boolean function of the 3 inputs it has. Now, so basically if you evolve the system, so you have 5 genes, and you have, so you have essentially 2 power 5 states, because each gene can take 0 or 1. And so you can have an attractor structure of this kind once you apply the logic rules recursively. And as you see, there are 3 fixed points in the system, and each of these fixed points corresponds to one particular subtype. Yeah, you can also have cycles, but then this particular model doesn't have cycles. So yeah. So the focus of my work is really on the Boolean functions. A lot of studies have gone into studying the network structure typically of gene regulatory networks and signaling networks, but not much research had gone into what is the nature of logic rules at these nodes. And so that is going to be the focus of my work. Right. So in order to understand better what is the nature of the logic rules, it's important to understand, one can actually look at different representations of logic rules apart from just looking at Boolean expressions. So the first one I'm sure everyone is familiar with is the truth table. So this is the truth table of a 3-input function. And so, so I denote by k the number of inputs, and the number of ones in the output column of any truth table is going to be called a bias. So this has a bias of 3 because there are 3 ones in the output, and this is also called as, I'll simply call it as an odd biased function. So you can have an even number of ones in the output, that would be called as an even bias. The next one is already something which we have seen, is the Boolean expression, where you have literals and you have, yeah. So this is a particular DNF corresponding to this truth table. So each of these clauses is basically the rows corresponding, which have the output value of 1. And this expression can basically be factored to give a much smaller expression like so. The last representation of the Boolean function which would be useful for us is the hypercube. So each of these vertices of this cube is one row of the truth table, and the color associated with the vertex is the output value. So red colored vertices are the input combinations are, have the output value of 1. So it's easy to see that the total number of Boolean functions for a k input function is 2 power k exponential and exponential in k. So this basically, so if you go to 5 input functions, you essentially have of the order 10 power 9 functions which you could assign. So now it's important then to ask, out of the space of all possible Boolean functions, are there smaller subspaces of Boolean functions which are biologically more meaningful than others? Because then, one doesn't want to explore all possible cases and wants to ask if there are, smaller subsets which are more meaningful. And so that is the first problem that we address, is that what are the possible types of regulatory logics which are more biologically meaningful than others. So I'll illustrate this particular the space of biologically meaningful functions using the space of all 4 input functions, though this is not specifically restricted to 4 input functions. So one can imagine the space of all 4 input functions is this huge square, and then you can divide it equally into functions with even and odd bias. So bias, remember, is the number of ones of the output column of the truth table. Then you have effective functions. So what is an effective function? I'll define that by defining what is an effective input. A function, a Boolean function is said to be, an input x1 here is said to be effective if by keeping x2 and x3 fixed and you flip x1, for some combination of x2 and x3, you will flip the output x4. So that's an effective function. And you can see here that effective functions occupy a huge space of the Boolean functions, whereas there's a small space of functions occupied by the ineffective, and they always lie in the even bias. And this is true for all values of k. Then you have canalizing functions. So an input is said to be canalizing. So the input x1 here, for instance, is said to be canalizing if when it takes the value c1, it fixes the output of the Boolean function to O1, irrespective of what x2 and x3 are. So it is like a veto function in some sense. The next class of function is the unate functions, which is also called as the monotonic functions. So if one focuses on x1 and x4 here, x1 is an activatory function in the sense that if you increase x1, you either increase x4 or you don't change x4. So you cannot increase x1 and decrease x4 because the relationship is activatory. So that's a unate function. Next is the read once function. In this function, each variable of the Boolean which regulate a particular gene appear exactly once. And you can have any combinations of parentheses in this expression. And the last class of functions we look at are the nested canalizing functions, which is basically an extension of the canalizing functions, in that if the first variable x1 did not take its canalizing input, then another variable, if set to a canalizing to a variable, would fix the output x4. So the take home from this particular figure is really not the shapes. The shapes of this is not important. This is just a Venn diagram made to look fancy. But the important part is at which places do each of these different classes lie, and what is the relative size of the different classes. So you see here that the NCFs are the smallest subspace in the space of all functions here. And after that is the ROFs, then you have the UFs, and then you have the CFs. And you see that also the ROFs and the NCFs always lie in the odd bias, and this is true for all values of number of inputs. Now, this is the theoretical space of all functions, but then the question has to be asked as to are there some types of these functions which are more enriched in real biological data sets? And so we then set out to construct, to collate a set of Boolean functions derived from 88 Boolean models which have been reconstructed till date. And from this 88 Boolean models, we extract all the Boolean functions and study them. So what is the first observation we make from this is that you can compute the in-degree distribution of this set of 2687 functions. And the first thing you observe is that most of them are odd biased functions. That is, the number of ones in the output column of the truth table for each of these functions is an odd number, which is actually surprising. If functions were chosen randomly, then you would expect that you would have an equal number of evens and odds, but this is otherwise. Then we look at how each of these different classes which I mentioned to you, that is the effective unate canalizing ROFs, NCFs, and non-NCF ROFs, how are these enriched in the real data set? And we find that indeed the ROFs and NCFs are highly enriched, and in fact that they are also relatively enriched, meaning that not only are they enriched in the space of all functions, but NCFs being a subset, say, of the CFs and UFs are also enriched within that smaller subspace, right? And so we've answered the second question then, are there some classes which are more enriched than others? Yes, NCFs and ROFs. Then the question is, what properties of these types of Boolean functions can explain this enrichment? So we perhaps thought that one could look at the complexity of these functions and then to explain, but then how do you define the complexity? Is there a quantitative way to do so? And so we resorted to the computer science literature to borrow some measures from there and apply them over here. So the two measures of complexity we look at are the Boolean complexity and the average sensitivity. So what is the Boolean complexity? It is the number of literals in the shortest formula equivalent to some given formula. So for instance, you consider the following expression. One can actually apply the laws of Boolean algebra and reduce it to a smaller expression here. Of course, and you just essentially count the number of literals in this expression. So here you have 5. X2 appears both in its negated and non-negated form. So you count both anyway. So the Boolean complexity of this expression would be called as 5. So if you take all 4 input functions, 65,536, and then you plot the Boolean complexity versus the bias, this is the plot that you would get. I'll mention here, there's a big caveat, which is that these are not exact computations, because of course this is a computationally intractable problem, computation of Boolean complexity. So this is only approximate, but what is true here absolutely is that the NCFs and the ROFs would have the minimum value. That is, this is in some sense the measure of compressibility of a function, and you cannot compress the NCFs and ROFs further than this. So the ROFs and the NCFs basically have minimum Boolean complexity. Yeah, the next quantity is we look at, but if you notice, this doesn't distinguish the NCFs and the non-NCF ROFs. And so we needed to look at some other measure of complexity, and we look at the average sensitivity. So what is the average sensitivity? For that we need to define what is the sensitivity. Sensitivity is defined at any vertex of the hypercube, which is a row of the truth table. So the sensitivity of the vertex 0, 0, 0 is basically the number of neighbors which are different from itself. So 0, 0, 0 has only one neighbor which is different from it in terms of its output value. So the sensitivity of 0, 0, 0 is 1. Similarly, one can compute the sensitivity of all the other vertices, and you can get the total sensitivity and the average sensitivity, which is basically the average over the total number of vertices. And so then what we did is that this is an exact computation, so there is no problem here. And so one can essentially do a calculation of all the 65,536 functions again and see how these different types of Boolean functions, where do they lie in this. Very interestingly, if you notice that at each of these odd biased values, you can look at all these triangles, these are the NCFs. And whereas the ROFs are rectangles, squares, and they are sort of above the NCFs. And so this measure sort of distinguishes the ROF and the NCF, or rather the non-NCF ROF. And so then this made us to really conjecture, this led us to conjecture that the NCFs have the minimum average sensitivity for a given number of inputs and for any odd bias. And so the last slide is really to show that this is indeed the case, that there exists a theoretical proof that one can show that for any value of k and for any odd bias, the NCFs actually minimize this average sensitivity. And so it basically amounts to finding some arrangement of these p vertices such that you will minimize the average sensitivity. But this problem can be transposed to something else, which is basically counting the number of edges between the vertices which have output value of 0 and the output value of 1, and trying to minimize those number of edges basically. But this particular problem we found had been solved in 1976 by Sergio Hart, and in this particular paper called A Note on the Edges of the N Cube. And he had solved this problem basically, and because that solution was available, all we had to do was to show that the solution he provided was equivalent to an NCF. And that's what we really show. And so his solution is basically called a good set of vertices. So what is a good set of vertices? So if you have, if you want to look for p vertices on the hypercube,
which would minimize this average sensitivity, you essentially have, you will say that P lies between some 2 power r and 2 power r plus 1. And then you would choose this an r plus 1 dimensional cube, break it into 2 vertex disjoint subsets of r cubes, and fill one of those with P vertices. And then you repeat this process recursively on the other r cube. And so, so that's really the result. And so finally, what are the properties or features of Boolean functions that could explain the enrichment of ROFs and NCFs in the empirical data set is the minimum Boolean complexity and the minimum average sensitivity. And so therefore, my title, which is that simple regulatory logics appear to drive complex cellular decisions. So there's a reason why I have the word appear here, specifically because the empirical data set which we look at is not free from subjective biases at some level. And so it's important to use the word take a pinch of salt and make the conclusion. And so I would like to thank my PhD advisor, Professor Arijit Samal, and our collaborator, Professor Olivier Martin. And this paper is a published piece of work. And if you would like to have a more detailed discussion and give more criticisms, feedbacks, whatever, you're free to visit my poster, which is also put up. And I would like to end finally by this quote by Leonardo da Vinci, which is that simplicity is the ultimate sophistication. Thank you.
Make it 7:25, then people will actually come in by 7:30. Yeah. No, so we are, yeah. So 7:25. Please try to come on time. It's been a long day, and we are looking forward to the talk. So please do come back on time. Thank you.
Okay, welcome for the last session of today, everybody. And it's a pleasure to introduce Professor K. Vijayaraghavan, who doesn't need introduction, but I'll do it briefly. So he's one of the foremost Drosophila biologists working on neurogenesis and myogenesis, which is, I think, what he'll be talking about today. Former director in CBS, former DPT secretary, former principal scientific advisor to the government of India, Padma Shri, Infosys Prize winner, Royal Society fellow, and so on and so on. I met him in, I think, 2004 when I was 31 and unknown to the biology community in India. I had done my PhD in physics, and he met me at some meeting in Mahabaleshwar and immediately reached out for a possible collaboration, which happened. And that's the kind of person he is. In 2012, when we were talking about setting up a computational biology group at IMSC, he was extremely supportive and helpful in many ways. And as DPT secretary and as PSA, he was engaged with the public via social media as well as via private channels. And though not all inputs could be acted on, I think all were read and engaged with. And he was in the hot seat during COVID, and despite the difficulty of herding cats and so on, he made a lot of important contributions, like ensuring some level of open data sharing and so on, and ensuring some scientific input into what drugs were prescribed, things like that. So anyway, without further ado, here he is.
Yeah. Thank you very much, Rahul. It's a great pleasure to be here. There's only one thing worse than being an after-dinner speaker, and that's being a before-dinner speaker. Before dinner, all of you are awake and can throw metaphorical tomatoes and eggs at me. After dinner, that wouldn't be a problem. So congratulations on your 60 years. It's really wonderful to be here. I enjoyed the talks, all of today. And I must say, my interaction with mathematicians and theoretical physicists has a history which goes back to my time as a student and faculty member at TIFR. It was absolutely wonderful. The physicists could see through biologists, so they didn't think too much of them. I remember B.V. Srikantan telling Pavitra Maitra when Maitra accosted Srikantan about some serious problem that, Pavitra, you will not understand, you're a biologist. But the mathematicians, because they knew less of biology, had no prejudices about biologists, and so we became good friends with the mathematicians. Not that we were not friends with the physicists. And I remember being very impressed by seeing M.S. Narasimhan writing in the air, and even more impressed by C.S. Sheshadri writing in the air and then erasing it. So these were very impressive people. Balu talked to us this morning about Ramachandra. I was in the hostel at the same time as Balu, and sometimes he would be at the next stall in the shower, and Ramachandra would be outside the door, and they would be conversing. And this was not a irregular feature. It's quite common because it happened many times. So the mathematicians were very interesting, and it's really wonderful to see how math science has grown, and the area of science in Chennai in general has grown, and we'll learn more about that. So on to my talk. I'll be talking about cells, circuits, and the developing brain. And really the principal issue which I'll try to address is how stars function they do. But if you look at, can you dim some of these lights here, if possible, but otherwise don't worry. Because some of the other figures may be a little better with lower light in the front. So, if you look at a tiny bacterial cell, such as that of a well-studied bacterium, the Escherichia coli shown here, it's about 1 cubic micron, and the volume of the cell body of a typical neuron, a nerve cell, is about 12,000 times more than that. And in a motor nerve, such as what we have, or elephants, or dogs, or cats have to control our muscles, the axon itself can stretch up to a meter or so without any problem. So the issue is that this nerve cell is extraordinarily complex, much larger than a bacterial cell, and we know rather little about bacterial cells. in many ways. They sense the environment just like a nerve cell does and responds to it, but our ability to predict what the bacterial cells can do is not high, despite a lot of research. I mean, we can clamp all inputs and vary only one and see what happens, but if you start varying multiple inputs, our predictability goes down substantially. It's not that, it's only a problem that nerve cells, for example, have interactions with other cells. Our cells and other cells in our body interact with multiple cells. Bacterial cells also do that, and that's been studied very nicely. Groups of cells will communicate with each other. A small number of cells will tell more bacterial cells what to do as a community and what not to do. So cell-cell communication on scale is not just unique to organisms such as us. It's there in multiple other, even in single cellular organisms. So despite this, as I said, studies of over 100 years have, and how cells respond to all kinds of environments, different kinds of cells, have dramatically increased our understanding of the processes involved. So at least at a descriptive level, we know a lot. And at a mechanistic level, we know a lot about the components. Yet, it would be fair to say we are not fully able to move from understanding components of the complexity to be able to predict responses to multimodal inputs. That is when many changing parameters are simultaneously sensed by a cell. So these kinds of situations, if they're so difficult, the question then arises, how then can we understand a structure such as the human brain? And the human brain, of course, and all the wonderful things that humans seem to be able to do, but also how, for example, other questions such as how the mind relates to the brain. To answer this, and not just leave it as a rhetorical question, we must appreciate the complexity of the human brain and then see how it can be teased apart into components which we can address. Our brains have about 85 billion nerve cells, and they make about 1 trillion connections. While different parts of the brain have specialized function for vision, smell, motor action, and so on and so forth, the parts also communicate with each other, and they do it at multiple layers. So, there's an architecture issue and recursive interaction issue and so on. So there's an enormous amount of input information being analyzed and reanalyzed and fed back at multiple layers. So it's a very complex computational problem as also an anatomical and a physiological problem. So how will our understanding of the brain improve? And Sidney Brenner, one of the most brilliant biologists of our recent times, said that biologists, no matter what the problem is, they ask only 3 questions. That's okay, that's fine. It's just a blank slide. Yeah. So I was told about how to give talks that it's good to have a blank slide so that you can concentrate on what I'm saying and not on what's there. That it always then results in the IT people running up to fix the problem. So it's not good advice. So Sidney Brenner said that, there are typically biologists ask only 3 questions. Where did it come from? That's evolution. How is it made? That's developmental biology. And how does it work? That's physiology, biochemistry, and so on. Of course, if you're a medical doctor, you ask, how do you fix it when it's broke? So our ability to do these 3 things has changed dramatically, particularly in the last decade or so, but over the last 2 or 3 decades, enormously. So our ability to collect data at every level, what the genes are, where they're expressed, how the genes vary, how different components are made by genes, how gene regulation takes place, metabolites in every cell at every time, how connections are made, and so on and so forth. There's an enormous amount of data which is coming in, and that kind of data far, far exceeds what we're collecting from, for example, astronomy and high energy physics and so on. So this is a very big challenge where we're flooded with data and we're short of theory and we're short of concepts. So that's an important thing going forward. So let's go through the first part. Where are we from? Where is the brain from? Where is it from? Now the Earth was born a little over 4.5 billion years ago, and the sun and the solar system was born a little earlier. only a little earlier, amazingly. And amazingly, life on Earth originated not too long after the Earth was born. We don't know yet how life on Earth originated, and that's a very important problem. There are very interesting theories and experiments going on. But we do know that about 3.5 to 3.8 billion years ago, simple cells, what are called prokaryotes, came to being. And about 3 billion years ago, there was photosynthesis, the ability to use light to generate energy, the sunlight. 2 billion years ago, complex cells, more complex cells resulted, what we call eukaryotes. And about 1 billion years ago, and maybe the dates are being pushed back now, multicellular organisms consisting of more than one cell, multiple cells originated. So it's, from 3.5 billion years to 1 billion years, amazing changes took place. Going further, 600 million years ago, we had simple animals. Then you had more complex animals, about 570 arthropods. There's a huge explosion of complexity. And we don't know how from these simple multicellular organisms to complex organisms, mechanistically what happened which allowed this dramatic explosion. There are lots of theories. And then you had fish and amphibians and so on and so forth. And about 400 million years ago, you had insects and plants. And about 360 million years ago, amphibians. About 130 million years ago, flowering plants. So the world was changing dramatically. Then 65 million years ago, something very interesting happened. We think an asteroid crashed or a meteorite crashed on Earth near Mexico, and that really resulted in a dramatic change in the landscape of life on this planet, eliminating dinosaurs and many large animals, and leading to the beginning of this dominance of mammals on this planet. So 65 million years, non-avian dinosaurs died out. 2.5 million years ago was the appearance of Homo, and about 200,000 years it's since the appearance of modern human, and only 25,000 years ago Neanderthals died out. Now, as a consequence of our evolution, and then as a consequence beginning sometime maybe about 10,000, 50,000, 100,000 years ago, in that range, many things happened. Early on in our evolution, we got the ability to oppose thumb and forefinger, make tools. And then as our brains grew disproportionately to our body size, or at least were over-designed compared to what our bodies immediately needed, we evolved the ability to speak and link speech and language to cultural activities and functions. So sociological and cultural evolution rapidly overtook biological evolution. So today, we are in a situation, not only do humans understand nature's engineering substantially and keep doing that, but we have become the engineers of nature. And we today, as philosophers have said, wield the paintbrush on the planet of the Earth, on this planet, and hold the planet's future in our hands, not just our future. And therefore, we have become, we do things which it's impossible for other animals to do, such as go to outer space and so on and so forth. So the software and hardware of our brains, of course, is impressive, and our cultural evolution is extraordinarily impressive. So when we ask where all this came from, that's evolution. But we can also ask, how did this happen? And here, the common origin of all life on Earth, as far as we know, all life on Earth has a common origin. Chemistry, and it means that that shared, and we know now that that shared chemistry is tied together by the string of DNA. And as you heard these talks in biology just now, you can study any organism and have lessons for any other organisms because of this shared thread of chemistry and the way DNA ties it together. So how is it made if all this is tied together by the shared chemistry? There, it's actually very interesting. Because of the shared chemistry, there's also a shared toolkit. And rather than study to functions, different tissues and humans are made, biologists typically study simpler organisms and study brains in much simpler organisms. Now, that has resulted in getting enormous information which can be applied to other organisms. So here's a simpler organism. Now, it's not these simple organisms, that's just a joke slide, are organisms which can be manipulated in the lab. These have a smaller number of neurons. For example, the fruit fly has about a few tens of thousands of neurons, 20-ish thousand. Other organisms, such as the worm, which Sandhya Kaushika here studies, has far less. And it's possible for us to understand how these neurons are made, how they are born, how they grow, how they connect, and what is the mechanism which leads to their function. Now, the simple rules of development are shared between all organisms, starting from a fertilized egg, which divides to give 2 cells, then 4 cells, and 8 cells, and so on. And you have, for example, during development, a sheet of cells, sort of like us in this auditorium. And these sheets of cells, maybe at some stage of their development, be identical to each other. And then differences arise from them, which make them into different parts of the organisms. So an identical sheet can change the properties of its units in broadly 3 different ways. Cells can be in contact with each other. You can influence your neighbor, and your neighbor can become like you. You can influence a small neighborhood, or you can influence a larger neighborhood. This is called the American model, where your success depends on where you live. Cells can also change their properties depending on who their parents are. And if you're born to a particular set of parents, you are like them, and that's the English model, where heritage matters more. And quite often, cells can be identical to each other, and one cell randomly becomes different from the others and suppresses everyone from success, and that's the Indian model. So these 3 models of development are what, and these have been understood at molecular terms really well, what are the kinds of molecules involved. But don't take me seriously about these models and quote me. I hope this is not being telecast live and something like that. Yeah. It is? Okay. So these kinds of molecules are used again and again in different contexts. And really, about 5 or 6 pathways which use these molecules are all what it takes to make cells different from each other. So groups of cells are similar. They signal at a short distance to make that block different from this. Then those signals within each other to create other kinds of differences, and so on and so forth. But the same toolkit is used again and again, typically within the organisms to make immune cells, brain cells, skin cells, and so on and so forth. And the same toolkit is also used between organisms. Multiple organisms use that. So this shared toolkit at a high end is very important and common. And because of the shared toolkit, because location matters, and where a cell comes from matters, and where they end up or migrate matters, you make all sorts of differences in different parts of the body, including different parts of the brain. So that's a very long story on how this can be done. It's very exciting. It's an area where there's an enormous amount of data coming in about understanding these systems better. But basically, it's a mechanism which uses a shared toolkit in diverse contexts in very different ways. And it's a big challenge to decipher that, but those tools for deciphering that are becoming more and more accessible and available. So you saw Leonardo da Vinci earlier, and here's another version of that, showing that, again, that you can study any organism and learn a lot about any other. There's, for example, a gene called Wnt, based on a fly gene called wingless, which is involved in many cancers. In the fly, its removal affects the wing. It was discovered in the undergraduate classroom in an agricultural research university, IARI in Pune, by Sharma and Chopra, and it really is an extraordinarily important gene for understanding how development takes place. So again, you don't know where value will come from in these situations. So that's how things are made. We learned about where they come from, where they're made, how does it work. That is physiology. And in terms of the nervous system, Hodgkin and Huxley took this giant squid, opened it up, took a giant axon from that, took the insides of the axon out and put in saline of various compositions there, and by altering currents, by clamping the neuron, as it were, could decipher what the properties of the neuron were, which gave rise to what we know is the action potential, the electrical signal, which propagates from one end of a neuron to the other. And this is absolutely extraordinary, because by just recording from a single cell, they could set up, they could decipher and put together a set of mathematical equations which are consistent with predictions of specific molecules which are involved in setting up these currents and potentials which propagation. Today, it is possible to record from nearly 1,000 nerve cells at the same time, collect large amounts of data. Many of these channel molecules and also the molecules which are involved in connection, the synaptic molecules, all of them have been identified by recombinant DNA methods. So our ability to collect information about function of many, many neurons at the same time is absolutely extraordinary. So we have a path through evolution to understand where various components have come from. We have, again, through evolution and developmental biology, we know how these complex tissues, including the brain, are made somewhat. There's a lot to know in both cases. And we know from physiology and our ability to use fluorophores, molecules which tell us about the activity of cells at different times, and also from anatomy, which tells us about connectivity, how connection and activity relate to each other. Now we have to figure out how to put all of this together and how function emerges during development and in real life. So that's the last challenge. How is it that we have such extraordinary sensory motor control, some of us, to deal with life, and how is it put together during development, and what are the mechanisms of how this takes place through sensory motor and integration in real life. And there have been extraordinary studies, again, both in looking at different organisms from the outside, humans and other organisms, and looking at other organisms which are tractable from the inside to see how the acuity of the sensory motor system is put in place and functions. So this is something absolutely stunning. You have to have young Ronaldo going in for training, practicing to become as good as he is. He's not born with that ability. But a fruit fly, on the other hand, is born with this ability to play football right away at birth. Doesn't have to go to any training school or do any such thing. So how does this ability come about? Now, how development puts together this ability is related to a way by which the animal makes different components. It tests these components in different ways. For example, in the development of rat hearing system, rat ear, as distinct from, for example, in terms of visual system development. Visual system development requires at birth for the animal to experience different visual cues, and then the system matures. The hearing system, on the other hand, has fictive cues to mimic hearing before the animal emerges, is born, and therefore there's testing of that capability and ready to go when the animal is born. So there can be different kinds of maturity in different animals or different tissues. Mountain goats, for example, have this ability to run up and down the side of the mountain as soon as they're born. Some other animals will take a long time to be able to walk. So the basic tenet seems to be that you put together the right connections, you test the connections in fictive manners or in real life, and then you bring them out and you're ready to go. You don't actually have, in many cases, testing out the animal after it emerges or it's born, though of course there's a huge amount of maturation in different contexts which takes place. Now this again has been studied really well in multiple brain projects all over the world. And these projects attempt to do things which were just unimaginable a short while ago. They chart out the connectivity in the entire animal, in the case of the fruit fly or the worm, or now people are trying to do that with zebrafish. It's a huge challenge. But these kinds of attempts to chart out entire connectivity of the brain runs into an enormous roadblock. The methods involved are electron microscopy of various kinds, and they can be rate limiting. They have to be both accurate as well as well done. Those technologies are improving enormously, but they are slow. But even when you have the EM sections, handling the data so that pixel by pixel you match between sections and do this segmentation analysis is a big challenge. There are major groups all over the world, big companies doing this through AI, so that's moving a lot faster, but not fast enough. And there are groups which outsource through large-scale crowdsourcing through students who actually do finish off and do a manual kind of completion of the segmentation analysis. And this has been done really well for the fruit fly, and the entire map of most of the fly's brain is now ready. So before this kind of segmentation, this is how it would look like on the left, and after that segmentation, you would get a much more detailed analysis. You have this wiring diagram of every neuron in the fly's brain, where it's connected, what the thousands of synapses it makes. But not only that, you can interfere with this wiring during development. You can record the function of each of these components in live flies, and you can activate or inactivate components. And you can look at behavior while you're doing this. So at least a documentation of what is happening everywhere, whether the input is one or multiple sensory inputs, is something which is extraordinarily feasible, and that's something which will now need to be examined from the perspective of hypotheses and mechanisms and how our understanding can improve. So this is an example of a completed annotation at really high resolution. So another factor which has happened is our ability to look at behavior in these contexts. Because you can manipulate every single nerve cell in these animals, you can do that and have these animals now moving around freely and see what they behave. And our ability to record multiple animals doing multiple things in different contexts, courtship, choice of odors which they like or don't, choice of food, mating, courtship, visual cues, all of that is just absolutely astounding what one can do at great resolution. And because of this mapping and because of this link of behavior to the inside of the organism, we can see from the outside and then also opening up from the inside what the organism is doing. So let's go back to the football fly. If you do this in slow motion and you label every point on its legs, you can see what it's doing. Because you know the position of every single muscle and every single motor neuron which innervates that muscle, from the outside you can say this is the muscle which is contracting or expanding. Then you can say, well, this is the motor neuron which must be coming on or switching off. You know where this motor neuron goes into the central nervous system. You know what other neurons connect to this, and you can start manipulating this and see what this happens. And you can invert this fly. It's now upside down on its back. You can put it on its feet, and it can move this ball, and you can show it a virtual reality of the world as it would be seeing it, and ask it to control that virtual reality. Keep some stripes within its vision, or go towards something which is attracting, go this other way, and see what neurons are doing what. It's really very, very impressive what that can be done. Now, that's impressive. So our challenge now going forward is this. Can we do this kind of work in larger organisms? What can we learn from doing this in fruit flies or worms or zebrafish even? What is it telling us new about the way the nervous system works? We have a checklist of all kinds of nerve cells, what kinds of neurotransmitters they make, how they connect, when they're firing, when they're quiet, what do they do at different times in development, when they think, when they sleep, when they remember. So that data is increasing at enormous speed. But what has changed about our fundamental understanding about how the brain works? We know a lot about the details of how cells work, somewhat about how groups of cells work, and what groups of cells are active or not at different times. But there's much, much to be learned. And one important question which many people ask, analogous to what the promises of the Human Genome Project was, that is such kind of large-scale brain ventures going to pay off or not, or is it a promise which is not likely to pay off? But in any event, it looks that the collateral benefits would be enormous, and the benefits in health, in declining mental abilities, and in development, in how brain development takes place, there are already great benefits, and I think we're going to see a lot more. So let me end by showing you this picture. This is made by Sanjay Sane many, many years ago. And what we're trying to understand is how the steering, not the powering of flight, how the steering takes place in collaboration, which we've just started with Sanjay Sane and Michael Dickinson. And the wing in the fly beats by the muscles inside turning the thorax. And here, there's a banana in one of these four pillars, and the fly is going around. It exquisitely moves all over the place, and precisely on the wrong pillar, unfortunately, in this case. But it does, of course, many times choose the right pillar. So how does this happen mechanistically in terms of sensory feedback from the outside world? What are the sensory nerve cells on the wing and on the body of the fly? What's it telling? And the eye and smell, how they all come together to make the fly do this is very exciting, of course. But how it is made is something which is relatively, and lots of groups are studying that, but how it is made during development is something which also needs to be looked at, and that's what we're looking at, and also using comparative evolutionary approaches for that. So this is something which, as we learn more, we will probably know that we know less, and there are many, many tools to look at this. But right from how the brain is, where it evolved, how it is made, and how it functions, but also how the software of the brain is put together by us to result in massive cultural and social changes which we have brought upon this planet. We have moved from being on the planet of the apes to being on the planet of the apes. We have got an extended phenotype. We can do extraordinary things which other animals cannot do. How did that software ability come about is something which is very exciting, and I think this will be a lot of work which will go ahead on that. Thank you very much.
Thank you very much, Vijay. And I know you're all waiting for dinner, but I think some of you are even more eager to ask your questions. So let's have it open for 5 minutes, and then we'll do dinner. Special honor for you. Or maybe not. Anybody?
So is it true that the organism can do like this smooth flight? Is it that there are more connections already made in the brain before?
System hasn't taken place. It has.
Just after, being born.
No, that's pretty impressive. A mountain goat or a horse can, run around soon after they're born. And how that system is functionally put together is extraordinarily impressive. We know, at least I'm aware of studies on how that happens in flies and so on and so forth, in maggots of flies and so on. but I don't know of studies which look on how that developmentally is put in place to have function over there. But its function is very impressive. Yeah. Yeah, but a fly can fly when it's right after it's born. A dragonfly can mate in midair, which we need an aircraft to do. So they're very impressive insects.
How much knowledge are we actually getting? That's a philosophical question, but in neuroscience in particular, the overwhelming.
This has been a topic of much debate, and that keeps getting rekindled when new tools become available. One, the collection of big data. The other tools are using deep learning, machine learning, AI, and so on and so forth. Brenner, in his article about a few years ago, I think it was on Turing's 100th birthday, is it possible? Yeah, he had a nice set of articles, it's worth looking at those. Basically, he says that, look, there are a set of people who bemoan the onslaught of big data and say that in our good old days, this wasn't the case. We had deep thinking, and we used to come up with good hypotheses and solutions to problems, and now it's all collection of data. He says that's wrong, that you shouldn't bemoan the onslaught of data, you should welcome it. But you also need theory and an understanding of different domains in biology in depth to be able to link that into what is actually happening. And in some areas, this has grown enormously. In brain research, it is growing really well. There are overall, crudely put, there are two approaches. One is bottom-up, where you try to build circuits and get them to function, and brains and so on. That's informative. And the other is to break it down and see what happens, and try to see how machines can deal with these kinds of issues. So I think it's a new age, and a new set of approaches. And as happened in physics, for example, you're going to see now increasingly theory and experiment exchanging places in ways taking the science forward.
Sorry if I'm not phrasing the question correctly, but our attempt to understand the neurological processes and how the neurons interact and so on. So will it have a sort of a impact our understanding of the healing process? And then at some point in the future, is it likely that we will be able to simulate this healing process like the way medicines do at a chemical level? But can we teach the brain to sort of heal itself in whatever way?
Right. So there are two components. This is a very interesting point. One is, how does the brain, when damaged, heal itself? And there's an enormous amount of work which has been done in patients, in humans, who have various kinds of functional deficits or don't have it, to see what's happening. And it's pretty impressive to see how compensatory mechanisms can come. For example, there are compensatory mechanisms which come after strokes, after spinal cord injury, other kinds of injury. Recently, there was much fanfare about a study of a boy who, it turned out, was born without a cerebellum. The entire cerebellum was missing. And the boy is pretty much reasonably normal because, again, of what I mentioned, the extended phenotype, that family and friends and instruments compensate in many ways for what the cerebellum does. So these kinds of external prosthetics, just as we have hearing aids and spectacles and walking sticks and so on, these kinds of mechanisms of feeding back into brain dysfunctions will also be part of the healing. The principal problem in intervening for healing in the brain relates to this shared toolkit I mentioned. If every major item is used in every kind of cell, if you want to mess around with one part because there's dysfunction there, by putting an inhibitor or an activator of some component, and you're putting that drug in the entire system, you're messing it up everywhere else. So if it's a terminal illness, side effects being really bad doesn't matter because you can recover somewhat. But if not, it's a big challenge about effectiveness of drugs and drug delivery to particular targets. But there are very nice efforts now which can target not only drugs to specific groups of cells, but specific parts of cells, and then optogenetically or optically activate them in a manner which allows them to function locally. So again, there are new ways of healing which are happening. They're currently expensive, but I would keep in mind that there was a time about a few decades ago where a cochlear transplant, which would transform the lives of many people, was several $100,000. And now it's available for close to $1,000 in that range. So, and it's widely available, insurance companies will pay for it, and so on and so forth. And similarly, if you look at the history of spectacles, they are now very widely available for various kinds of purposes. So this is going to, as demands of an aging population increase, you're going to see a lot of interventions of this kind.
Okay, let's thank Vijay once again. And before we leave the stage, there's a memento for you.
Thank you. Yeah, I think I will. Something quick.
I'm sure there are more questions, but you can have them with Vijay over dinner. And he's also here tomorrow, I think, at least part of the time. And yeah, so bon appetit, everyone, and see you tomorrow.